Tonight, let's begin with something simple. When we ask how far human civilization can really go, we first have to ask a quieter question. Where are we right now? Not where we hope to be, not where we imagine we are, but where we truly stand. In 1964, a Russian astronomer named Nikolai Kardashev proposed a simple way to measure civilizations. He didn't measure them by intelligence, not by art, not by kindness, not even by technology alone. He measured them by energy. Because when you look closely, energy is behind almost everything we call progress. Every city glowing at night, every airplane crossing the sky, every phone lighting up in someone's hand, every server humming quietly in a data center the size of several football fields, placed side by side. All of it runs on energy. So Kardashev asked a bold question. What if we ranked civilizations by how much energy they can control? Not just produce for a moment, but control, direct, and use whenever they want. He imagined 3 main levels. A Type 1 civilization controls all the energy available on its home planet. A Type 2 civilization controls the energy of its star. A Type 3 civilization controls the energy of its entire galaxy. It sounds dramatic at first, almost like science fiction. But if you strip away the scale of it, the idea is simple. How much power can a civilization command? So where does humanity fall on this scale? You might think we're already at Type 1. After all, we have global communication. We can split atoms. We send machines to other planets. But when scientists estimate our level, we're not even at Type 1 yet. We are roughly Type 0.7. That number may sound abstract, so let's make it clearer. A Type 1 civilization would use all the energy that reaches its planet from its star. For Earth, that sunlight is massive. Every hour, the sun sends more energy to Earth than humanity uses in an entire year. Imagine sunlight pouring down like an endless waterfall. We are only catching a thin mist at the edge of it. Right now, most of our energy still comes from burning ancient sunlight. Fossil fuels formed from plants and organisms that lived millions of years ago. It's like we're running our entire global system on a savings account that took hundreds of millions of years to build, and we're spending it in just a few centuries. We don't fully control the ocean's power. We don't control global weather. We don't capture all available solar energy. We don't even manage our own planet's system smoothly. In fact, we still struggle with power outages during storms. Entire cities can go dark because of a single damaged line. That alone tells us something important. If a civilization cannot keep its lights on during a strong storm, it hasn't mastered its planet yet. So what does 0.7 really mean? It means we have advanced tools but limited control. It means we are clever but not yet stable. It means we can send a rover to Mars, a machine the size of a small car driving across a dusty world tens of millions of miles away. Yet we still face energy shortages and environmental strain at home. There's something humbling about that. We've built skyscrapers taller than 1,500 feet. That's taller than stacking 4 football fields upright. We've created rockets powerful enough to escape Earth's gravity, pushing with force stronger than millions of car engines roaring at once. And yet, we still depend on burning coal in many places. So are we advanced? Yes. Are we powerful? In many ways, yes. But compared to what may be possible, we are still at the early stages. It's like we've just learned how to make fire, and we're only beginning to understand how not to burn ourselves. You might wonder, if we are only at 0.7, how far is Type 1? To move from 0.7 to 1.0 doesn't mean doubling our power, because the scale is logarithmic, which simply means each small step requires a huge increase in energy. Going from 0.7 to 1.0 would mean multiplying our energy use many times over. It's not like walking a few extra steps. It's more like climbing from the ground floor to the roof of a tall building without an elevator. And that raises a quiet question. Can we do it? Because reaching Type 1 is not just about building more power plants. It's about surviving long enough to build them. It's about managing climate, resources, conflict, and technology without collapsing under our own complexity. If a civilization destroys its own environment, it never reaches Type 1. If it tears itself apart through conflict, it never reaches Type 1. If it creates tools it cannot control, it may never advance further. So when we talk about how far human civilization can go, we must first accept that we are still in the early chapter. We are not masters of Earth. We are learning. We are experimenting. We are balancing on a thin edge between growth and instability. But there's something quietly beautiful about that, because being at 0.7 means the story is still open. It means the road ahead is not yet decided. We are advanced enough to understand the scale of the universe. We can measure stars that are trillions of miles away, distances so vast that even light, moving faster than anything else in nature, takes years to cross them. If you could drive a car to the nearest star at highway speed, it would take you tens of millions of years without stopping for fuel. And yet here we are, a species that only began using electricity widely about 150 years ago. Not even 2 human lifetimes stacked end to end. That's like a newborn baby trying to imagine adulthood. So maybe 0.7 isn't small. Maybe it's remarkable. In just a blink of cosmic time, we've gone from stone tools to global networks, from staring at the stars to sending machines among them. But the scale reminds us of something important. We are not finished. We are not at the peak. We are still becoming. And the question that gently lingers is this. If this is only 0.7, what might 1.0 look like? And beyond that, how far could it really go? As we move forward, feel free to share where you're listening from, or leave a quick thought below. And if this channel means something to you, subscribing is a small way to support the journey. When we hear the word advanced, what do we picture? Do we imagine intelligence? Do we imagine wisdom? Do we imagine kindness? Or do we imagine tall cities glowing at night, spacecraft leaving the planet, machines thinking faster than any human mind? It's easy to mix these ideas together. We often assume that a more advanced civilization must also be more moral, more peaceful, more enlightened. But the Kardashev idea measures something much simpler: energy. That may feel almost disappointing at first. Why energy? Why not compassion? Why not art, or philosophy, or happiness? The answer is quiet and practical. Energy is the foundation of everything physical. Every building, every road, every data center, every hospital, every farm, all of it requires energy. Even the device you're listening on right now is powered by energy stored in a battery or flowing through wires. Without energy, everything stops. Screens go dark, water stops flowing, heat disappears. Energy is like the blood of civilization. So when we talk about advancement in this framework, we're not talking about being smarter. We're talking about controlling more power safely and consistently. Think of it this way. If a village uses firewood to cook meals, that's energy control at a small level. If a city runs on electricity from a massive power grid stretching hundreds of miles, about the distance of driving across several provinces without stopping, that's a larger level of control. If an entire planet captures nearly all the sunlight that touches its surface each day, storing it, directing it, and using it whenever needed, that is something entirely different. So, advancement here is about scale. How much of the available energy can be harnessed? And that raises a gentle question. Does using more energy automatically mean progress? Not necessarily. A civilization could waste enormous energy and still struggle. Imagine leaving every light on in every building all day and night. That increases energy use, but not wisdom. So the real meaning of advancement is not just producing energy. It is controlling it. Control means stability. Control means reliability. Control means you can turn power on and off like flipping a switch. And it works every time. Right now, humanity uses about 18 terawatts of power on average. That number sounds abstract, so let's picture it. Imagine 18 trillion watts. 1 trillion is 1,000 billion. It's hard to feel that size. So instead, imagine this. It's like running billions of hair dryers at the same time, across the entire planet, every second of every day. And yet, compared to what Earth receives from the Sun, that's still tiny. The Sun sends about 170,000 terawatts to Earth continuously. If our energy use is 18 terawatts, we're using only a tiny slice of what arrives freely every single day. It's like standing under a waterfall wide enough to cover a city block and filling only a few buckets. So why don't we just capture more? Because collecting energy at that scale requires infrastructure, massive solar arrays, storage systems, global grids. It requires coordination across nations. It requires stability over decades. And stability is harder than invention. We have brilliant engineers, we have powerful machines, but managing a planet of 8 billion people, that's like coordinating the movement of every person in dozens of massive cities, all at once, every day, without conflict or error. Advancement in this sense is less about clever ideas and more about long-term consistency. You might wonder, could a civilization be very intelligent, but low on the scale? Yes. A society might create beautiful art, deep philosophy, and even advanced mathematics, yet still rely on small amounts of energy. In that case, it would remain lower on the scale. The scale doesn't judge culture. It doesn't judge goodness. It only measures how much power is under control. And there's something revealing about that, because when we imagine going far into the future, building structures in space, traveling between stars, reshaping planets, all of those dreams require enormous amounts of energy. To lift something into orbit takes huge force. A single large rocket launch burns fuel equivalent to what thousands of cars might use over years. And that's just to send a few tons of equipment into space. Now imagine moving millions of tons, or building habitats large enough to house cities in orbit, structures wider than entire stadiums. Without energy control, none of that happens. So when we ask, how far can civilization go? We are really asking how much energy can we command without destroying ourselves in the process. Because energy is powerful. Too little, and society struggles. Too much, misused, and it becomes dangerous. Think about nuclear energy. In a controlled reactor, it can power cities for decades. In an uncontrolled reaction, it can destroy a city in seconds. The difference is not intelligence, it's control. So advancement is about balance. It's about increasing power while increasing stability at the same time. That may sound slow and steady, and in truth, it is. Real advancement is not flashy. It's quiet. It's building grids that don't fail. It's designing systems that last 50 or 100 years, longer than many of us will live. It's thinking not just about the next decade, but the next century. And here's a softer thought. Energy control also reflects cooperation, because on a planet shared by billions, no single group can manage global energy alone. Power lines cross borders, weather patterns cross oceans, resources are scattered unevenly. So advancement in energy naturally pushes toward coordination. You cannot become Type 1 by acting as dozens of isolated islands. You must begin to function more like a single system. Not identical, not uniform, but connected. So perhaps the Kardashev idea is not only about machines and power plants. Perhaps it quietly asks whether a civilization can organize itself at planetary scale. And that brings us to an even deeper question. Is the limit to advancement technical or social? Do we lack the tools? Or do we lack the unity to use them wisely? Because if energy is the measure of reach, then survival is the gatekeeper. And before we can climb from 0.7 to 1.0, we must first remain standing long enough to try. If reaching Type 1 is about mastering the energy of an entire planet, then the real question becomes very simple. Can we survive long enough to get there? It's easy to imagine the future as a smooth upward line. More technology, more power, more reach. But history doesn't move in straight lines. Civilizations rise, civilizations fall. Some last centuries, some collapse within decades. If you look back just a few thousand years, which is a very short time compared to Earth's 4.5 billion years, like a single grain of sand compared to an entire beach, you'll see empires that once seemed unstoppable disappear completely. So what stands in our way now? The first barrier is climate instability. Our planet is like a carefully balanced system. The atmosphere is thin, only about 60 miles thick before it fades into space. 60 miles may sound large, but if Earth were the size of a basketball, the atmosphere would be thinner than a sheet of plastic wrap. That thin layer controls temperature, weather, and life itself. We are changing it. Burning fossil fuels releases gases that trap heat. The planet warms. Ice melts. Weather patterns shift. Storms grow stronger. A warmer planet is not instantly unlivable. But it becomes harder to manage. Agriculture becomes less predictable. Coastal cities, some home to tens of millions of people, face rising seas. Imagine water slowly creeping up over decades, covering land where entire neighborhoods once stood. Can a civilization become stable enough for planetary mastery while its environment grows less stable? That's one challenge. Another is geopolitical conflict. Humanity is not one unified system. We are many nations, cultures, and interests. Cooperation exists, but so does rivalry. Advanced technology spreads quickly. Weapons become more powerful. A single nuclear device can release energy equal to millions of tons of explosive force, like detonating thousands of large bombs at once. So the barrier is not only physical resources, it's trust. Can a civilization coordinate globally without falling into large-scale conflict? Because Type 1 requires planetary systems, energy grids that span continents, weather monitoring that connects every region, resource sharing across oceans. If trust breaks down, cooperation weakens. And without cooperation, global mastery becomes fragile. Then there is artificial intelligence. AI is a tool, powerful, flexible, capable of processing information faster than any human brain. A modern AI system can analyze patterns across billions of data points in seconds. That's like reading every book in a massive library, the size of several city blocks, in less time than it takes to blink. That power can help optimize energy systems, improve climate models, and manage infrastructure. But it also introduces risk. If systems become too complex, if decisions are automated without clear oversight, mistakes can scale quickly. A small software error in one part of the world can ripple outward, affecting supply chains, power grids, communication networks. Complexity itself becomes a risk. Imagine balancing dozens of spinning plates at once. The more plates you add, the harder it becomes to keep them all from falling. Modern civilization is spinning thousands of plates: finance, energy, agriculture, communication, health systems, all tightly connected. That connection brings strength, but it also means failure can spread. There's also the issue of resource mismanagement. Earth has vast resources, but they are not infinite. Fresh water, fertile soil, rare minerals. These are spread unevenly. Some materials used in advanced electronics exist only in small amounts. Extracting them can damage ecosystems. If we consume faster than we replenish, shortages appear, and shortages create tension. So here's the quiet barrier: sustainability. To become Type 1, we must increase energy use dramatically, perhaps many times over. But we must do so without collapsing the systems that support life. It's like trying to upgrade the engine of a car while driving at full speed down a highway. You cannot stop the vehicle. Society must continue functioning. People need food, jobs, stability, and yet transformation must happen at the same time. Is that possible? It might be. Humanity has solved enormous problems before. We have reduced certain diseases that once killed millions. We've built global communication networks in just a few decades. The internet alone connects billions of people, like a nervous system wrapping around the planet. But speed can be a double-edged sword. Rapid progress leaves little time for adjustment. Another barrier is psychological. As societies grow more comfortable, curiosity can fade. Urgency can weaken. If daily life feels stable, the drive to change large systems slows down. Will we maintain long-term vision? Because becoming Type 1 is not a 10-year project. It's likely a century-scale transformation. It requires patience across generations. Leaders who may never see the final result must still choose to invest in it. That demands a kind of cultural maturity. And then there's the simplest barrier of all: survival. Pandemics, natural disasters, unpredictable events. Earth has experienced asteroid impacts large enough to change life forever. 66 million years ago, a space rock roughly 6 miles wide, about the length of 100 football fields, struck the planet and ended the age of the dinosaurs. Such impacts are rare, but not impossible. To advance, we must not only grow, we must endure. So the path to Type 1 is not blocked by a single wall. It's more like crossing a wide field filled with smaller obstacles. Climate, conflict, technology risk, resource strain, time. Each one alone might be manageable, but together they create pressure, and pressure tests resilience. So perhaps the true question isn't, can we build enough solar panels? Or can we develop better batteries? The deeper question is, can humanity remain stable, cooperative, and curious long enough to grow into planetary maturity? Because Type 1 is not just an engineering milestone, it is a survival milestone. And before we look toward mastering oceans, weather, and sunlight, we must first prove we can master ourselves. Imagine for a moment what it would really mean to master a planet, not to own it, not to dominate it in a careless way, but to understand its systems so deeply that energy flows wherever it's needed, smoothly and safely. A Type 1 civilization would control all the energy available on its world. On Earth, that energy mostly comes from the sun. Every second, sunlight pours onto the surface. If you could see it as a physical stream, it would look like a river wider than entire continents. And we are standing in it constantly. Right now, we capture only a tiny fraction. So what would change? First, solar energy would likely cover vast areas, not in a messy way, but in carefully planned networks. Imagine deserts, places already dry and open, covered with solar panels stretching farther than the eye can see. A single large solar farm today can span several square miles, about the size of a small town. Now imagine thousands of them, connected like pieces of a giant puzzle. But sunlight isn't constant everywhere. At night, it fades. In winter, it weakens. So how would a Type 1 civilization handle that? Energy storage. Batteries far larger than anything we use today. Storage systems the size of warehouses. Perhaps underground reservoirs storing excess power in different forms, like pumping water uphill during the day and letting it flow back down through turbines at night. It's similar to charging a battery, but using gravity itself as the storage tool. And solar is only part of it. The oceans hold enormous energy. Waves rise and fall endlessly. Tides move billions of tons of water every day. A single large ocean wave carries force strong enough to toss boats around like toys in a bathtub. Now imagine rows of wave energy devices anchored offshore, gently rising and falling with the motion, turning that movement into electricity. The ocean never truly rests. Even when the surface looks calm, energy moves beneath it. Then there is geothermal power. Deep beneath your feet, the earth is hot, very hot. Just a few miles down, temperatures can reach hundreds of degrees, hot enough to boil water instantly. Drill carefully, circulate water, let steam spin turbines, and you have steady power that doesn't depend on sunlight or wind. In a Type 1 world, these systems would not be scattered experiments. They would be fully integrated. Solar in deserts, wind across plains, tidal along coasts, geothermal in volcanic regions. It would feel less like separate power plants and more like one planetary engine. But energy production is only one piece. Mastering a planet also means stabilizing it. Right now, weather can surprise us. Hurricanes grow stronger over warm oceans. Droughts stretch longer in some regions. Floods overwhelm cities in others. A Type 1 civilization might learn to influence weather gently. That may sound extreme, but we already seed clouds to encourage rain in certain conditions. We already track storms from space with satellites orbiting thousands of miles above us. Satellites moving faster than a rifle bullet, circling Earth every 90 minutes. So the question becomes, could we go further? Could we reduce hurricane strength by cooling surface waters slightly? Could we guide rainfall towards drought-stricken areas? It wouldn't mean total control. Nature is complex, but deeper understanding could bring softer adjustments. And then there's planetary engineering. If sea levels rise, do we build higher walls, or do we redesign coastlines entirely? The Netherlands already lives below sea level in some areas, protected by massive systems of barriers and pumps. Now imagine that effort scaled across the globe. Cities might be redesigned for resilience. Buildings constructed to generate their own energy. Roads embedded with solar materials. Agriculture moved into vertical farms. Structures as tall as skyscrapers. Growing food indoors under carefully controlled light. Imagine food production rising upward instead of spreading outward, reducing pressure on forests. All of this sounds like an enormous effort, because it is. Becoming Type 1 would likely require multiplying our current energy production many times over, perhaps several times what we use today. That means expanding capacity while reducing waste. And waste matters. Right now, a lot of energy is lost as heat. Engines waste it. Transmission lines lose some of it. In a more advanced system, efficiency would improve. Less energy would vanish, unused. But here's a gentle question. Would mastering the planet mean changing it beyond recognition? Or would it mean learning to live within its patterns more intelligently? True mastery may not look like domination. It may look like harmony. Instead of fighting the wind, we place turbines where wind naturally flows. Instead of battling tides, we harvest their rhythm. There's also the idea of global coordination. Energy would move freely across continents. If it's night in one region, power flows from where the sun still shines. If winds are strong in one ocean, that surplus supports calmer regions. Picture a global grid, like a web wrapped around the planet, connecting everything. If you could see it from space, it might look like faint glowing lines crossing oceans and land, pulsing gently. But this requires trust and cooperation at planetary scale. No single nation could run a Type 1 Earth alone. So perhaps becoming Type 1 is not just about engineering. It's about maturity. Can we think as a planet? Can we plan not just for the next year, but the next 100? Because once Earth is mastered in this sense, energy flowing smoothly, climate stabilized, systems resilient, something interesting happens. For the first time in history, humanity would not be struggling to survive environmental instability. We would be standing on stable ground, and from stable ground, new possibilities open. But before we look outward, we must first finish learning how to power our own world. If a civilization truly masters its planet, something deeper must happen first. Not just better machines, not just larger power grids, but a shift in how it thinks, because controlling planetary energy is not only an engineering problem, it is a coordination problem. Right now, humanity lives as separate nations, cultures, and systems. We are connected. Yes, the internet links billions of people. Airplanes cross oceans daily, some flying distances longer than the width of entire continents in less than a day. But connection is not the same as unity. So here's a quiet question. Would becoming a Type 1 civilization require humanity to act more like a single organism? Think about your own body. Trillions of cells are working together right now. Your heart beats, your lungs move, your brain sends signals through nerves as thin as threads. Each cell has its own job, yet they cooperate so smoothly that you rarely notice. If one part of your body begins fighting another, illness appears. Now scale that idea up. 8 billion people, hundreds of nations, thousands of languages, different beliefs, histories, and priorities. Can such a system function as one coordinated whole? It may sound unrealistic, but in small ways we already see hints of it. Global weather monitoring involves satellites owned by different countries sharing data. Scientific research crosses borders. When a disease spreads, information moves rapidly between continents, sometimes within hours. It's not perfect, but it's a beginning. Planetary consciousness does not mean everyone thinking the same thoughts. It means recognizing shared systems. The atmosphere doesn't stop at national borders. Oceans don't check passports. Climate patterns move freely, like giant invisible rivers of air wrapping around the globe. If one region pollutes heavily, the effects can drift thousands of miles, about the distance of flying from Manila to Tokyo and back again. So to manage planetary energy and climate, decisions must consider the whole. You might ask, is that even possible? History shows that cooperation can scale. The International Space Station, for example, orbits about 250 miles above Earth, roughly the distance of driving from one major city to another in a few hours. It was built and operated by multiple countries working together for decades. That's not small, but planetary coordination would be far larger. Energy grids crossing continents, shared climate strategies, resource planning over generations. It requires long-term thinking. And long-term thinking is hard for humans. We tend to focus on what we can see. This year, this election cycle, this lifetime. But planetary systems operate over decades and centuries. Trees planted today may not mature for 50 years. Ice sheets melt slowly, like a massive frozen lake the size of several countries gradually thinning over time. So a Type 1 civilization might need a cultural shift toward patience. Patience doesn't mean slowness, it means consistency. Another question naturally appears. Would global unity erase cultural differences? Not necessarily. Think of a symphony orchestra. Each instrument sounds different. A violin doesn't become a drum, a flute doesn't become a cello, but they follow the same rhythm and direction. Perhaps planetary consciousness is more like shared rhythm than shared identity. It's understanding that survival depends on cooperation. There's also technology shaping this possibility. Instant communication allows ideas to spread in seconds. A message typed on one side of the planet can appear on another side almost immediately, faster than you could snap your fingers. This creates awareness. When disasters happen, people thousands of miles away can see it live. That visibility builds empathy. But technology can also divide. Information spreads quickly, both true and false, so maturity becomes important. A planetary civilization would need not just advanced tools, but shared trust in knowledge systems, reliable information, transparency. Otherwise, coordination weakens. You might wonder, has humanity ever acted as one before? In small ways, yes. During major global events, pandemics, space missions, environmental agreements, cooperation has occurred, but usually under pressure. The question is whether we can choose cooperation before crisis forces it, because waiting until systems are near collapse makes coordination harder. Here's another thought. Planetary consciousness might also mean emotional expansion, seeing yourself not only as a citizen of one nation, but as a resident of Earth. Astronauts often describe something called the overdue effect. When they look at Earth from space, a blue sphere about 8,000 miles wide, small enough to cover with your thumb if you hold it at arm's length, they feel a shift. Borders disappear, clouds swirl freely. The planet looks fragile. That perspective changes people, so perhaps widespread awareness of our shared home is part of advancement. It doesn't require perfection. It requires recognition. If we are to manage planetary energy systems, protect climate stability, and distribute resources efficiently, we must see Earth as one system. Just as your body doesn't ignore an injured foot because it's far from your head, a planetary civilization cannot ignore suffering in distant regions, because instability spreads. In a connected world, economic shocks ripple, environmental damage crosses oceans, health crises travel on airplanes. So unity is not idealistic, it is practical. And yet, unity does not mean eliminating competition entirely. Competition can drive innovation, it can push systems to improve, but competition without shared limits becomes destructive. So perhaps the future balance is cooperative competition, pushing forward while maintaining planetary stability. There's something calm about imagining humanity reaching that stage, not perfect, not uniform, but coordinated. A world where energy flows smoothly, climate systems are understood deeply, and decisions consider the long view. It may take generations, but if we cannot think as a planet, then mastering a planet may remain out of reach. And if we can, then something remarkable becomes possible. Because once a civilization can function as one coordinated system, looking beyond its world becomes far more realistic. Once a civilization learns to manage its own planet, a quiet restlessness often appears. What's next? For humanity, that question already echoes in our actions. We've walked on the moon. We've sent robots to Mars. We've placed telescopes in orbit that can see galaxies so far away that their light began traveling toward us before humans even existed. But visiting is not the same as living. So what would it mean to expand beyond Earth? Let's start close to home. The moon orbits about 240,000 miles away. That sounds enormous, but in cosmic terms, it's nearby. If Earth were the size of a basketball, the moon would be about 30 feet away, roughly the length of a small classroom. We've already traveled there. The journey takes about 3 days. That's shorter than many international trips by sea in the past, so building a permanent base on the moon seems possible. Why the moon? Because it has resources. Water, ice, hides in permanently shadowed craters near its poles. Water means drinking supply. It can also be split into hydrogen and oxygen, useful for rocket fuel and breathing air. And the moon's gravity is weaker than Earth's, about 1/6 as strong. Lifting materials from its surface into space would require far less energy. It's like jumping while wearing a heavy backpack versus jumping without it. A lunar base could become a stepping stone, a construction site for deeper missions. Then there is Mars. Mars is much farther, at its closest about 34 million miles away. That's like circling Earth, more than 1,000 times. Even at high speed, a spacecraft takes about 6 to 9 months to get there. Why go so far? Mars has similarities to Earth. It has seasons. It has polar ice caps. Long ago, rivers may have flowed across its surface. Could humans live there? Not easily. Mars has a thin atmosphere, less than 1% as thick as Earth's. The air is mostly carbon dioxide. Temperatures can drop to -100 degrees Fahrenheit in some regions, cold enough to freeze exposed skin in seconds. So living on Mars would require habitats, sealed structures protecting against radiation and cold. Think of domes or underground shelters, carefully engineered. It would be like living in a research station in Antarctica, but even more isolated and millions of miles away. Still, some argue that becoming multiplanetary increases survival chances. If Earth faced a catastrophic event, an asteroid impact, a global disaster, having settlements elsewhere could protect humanity from total extinction. But here's an important question. Should we expand before fully stabilizing Earth? It might feel tempting to treat Mars as an escape plan, but expansion does not remove responsibility at home. In fact, building colonies requires enormous resources. Rockets powerful enough to carry heavy cargo into space burn energy equal to thousands of airplane flights combined. Launch after launch, year after year. So perhaps expansion and stabilization must happen together. Beyond planets, there's another idea: orbital habitats. Instead of living on a planet's surface, imagine building massive structures in space itself. Picture a rotating cylinder, several miles long enough that driving from one end to the other would take several minutes. As it spins, artificial gravity forms along the inside surface. People could walk, grow crops, and live along its inner walls. These habitats could orbit Earth, the Moon, or even drift freely around the Sun. The advantage: no need to climb out of deep gravity wells. Materials from asteroids could be used to construct them. And that leads to another thought. Space is not empty in terms of resources. The asteroid belt between Mars and Jupiter contains vast amounts of metal, iron, nickel, platinum. Some asteroids are small, only a few hundred meters across, about the size of a large sports stadium. Others stretch dozens of miles wide. Mining even a single medium-sized asteroid could yield more metal than humanity has extracted in centuries on Earth. So instead of digging deeper into Earth's crust, a future civilization might turn outward. You might ask, how would we reach and capture an asteroid? Slowly. Robotic missions could attach propulsion systems, gently nudging an asteroid into a stable orbit closer to Earth or the Moon. It would take years, maybe decades. But in space, patience is normal. This expansion does not mean abandoning Earth. Earth would likely remain the cultural and biological center, the birthplace, but spreading outward reduces risk and increases possibility. Here's something interesting. The International Space Station orbits about 250 miles above Earth. That's closer than the distance between many cities within a single country. Yet living there requires careful planning. Every drop of water recycled, every breath managed. Now imagine scaling that experience up to cities in orbit, housing thousands or even millions. It may sound far away, but consider this. Just 120 years ago, powered flight didn't exist. The Wright brothers' first airplane flight lasted only 12 seconds, shorter than the time it takes to tie your shoes. Now we fly across oceans daily. Progress can accelerate quickly once systems align. So perhaps becoming multiplanetary is not centuries away. Or perhaps it is. The timeline remains uncertain. But one thing is clear: expanding beyond Earth is not simply about adventure. It's about resilience. It's about increasing the space in which civilization can operate. Because once a species no longer lives on a single fragile surface, once it spreads across moons, planets, and orbital habitats, the scale of its future changes. Earth becomes the starting point, not the limit. And when you begin to think beyond one world, the idea of harnessing an entire solar system starts to feel less like fantasy and more like the next quiet step. If humanity spreads beyond Earth, to the Moon, to Mars, to orbital habitats, one question quickly follows. Where will all the materials come from? Building cities in space requires metal, silicon, rare elements, water, fuel. On Earth, we dig into the ground. We carve mountains. We drill deep into rock layers formed over billions of years. But Earth is only one world. Out there, between Mars and Jupiter, lies the asteroid belt. It may sound like a crowded field of tumbling rocks constantly colliding, but in reality, the asteroids are spread far apart. If you stood on one asteroid and looked around, you likely wouldn't even see the next one without a telescope. Still, the total material there is enormous. Some asteroids are small, only a few hundred meters wide, about the length of 3 football fields placed end to end. Others stretch dozens or even hundreds of miles across, wider than entire cities, and many are rich in metals: iron, nickel, cobalt, platinum. On Earth, platinum is rare. A small bar of it can cost more than a car, but certain metallic asteroids contain more platinum than has ever been mined in human history. Imagine finding a mountain in space made mostly of metal. You might ask, why not just continue mining Earth? Because Earth's gravity is strong. Lifting materials into orbit takes enormous energy. It's like trying to throw a heavy object uphill out of a deep valley. Asteroids, on the other hand, have almost no gravity. If you stood on a small asteroid, you could jump gently and float away. A rock thrown upward might escape entirely. That means mining and transporting material requires far less energy. It's like working on a hill versus working at the bottom of a canyon. Water is also abundant in some asteroids. Water in space is extremely valuable, not just for drinking. It can be broken apart into hydrogen and oxygen, rocket fuel. So a water-rich asteroid becomes a refueling station. Picture a network of fuel depots scattered across the solar system. Spacecraft traveling between planets could stop, refuel, and continue. Just like cars on a long road trip. That changes everything. Travel becomes easier, trade becomes possible. But how would we mine an asteroid? We wouldn't send thousands of workers with pickaxes. Robots would likely do most of the work. Small, autonomous machines could anchor themselves to the surface. They could drill, extract material, process it on-site. Solar panels would power them, capturing sunlight that is still strong in that region of space. Material could be melted and shaped in microgravity. Without strong gravity pulling downward, large structures can be assembled more easily. You might wonder, how do you hold something steady in zero gravity? Anchoring becomes important. Machines would need to grip the surface firmly. Otherwise, pushing a drill into rock might simply push the machine backward instead. Space mining requires careful engineering, but the physics is not impossible. In fact, humanity has already landed probes on asteroids. Some have collected samples and returned them to Earth, traveling millions of miles with precision. So the technology is beginning. Now imagine scaling it up. If even one medium-sized metallic asteroid were mined, the resources could support construction of massive habitats. You could build structures kilometers long, longer than driving across a large city. Rotating habitats that create artificial gravity. Solar power stations floating closer to the sun, transmitting energy outward. The solar system becomes less like empty space and more like a vast resource field. And here's something interesting. The asteroid belt is not the only source. There are near-Earth asteroids, objects that pass relatively close to our planet. Some come within distances closer than the Moon, capturing one safely into a stable orbit. might provide decades of materials. But there's a gentle concern here. Would mining space create new risks? Possibly. Redirecting asteroids must be done carefully. A miscalculation could send an object toward Earth instead of into safe orbit. So precision and patience would be essential. Another question arises. If resources become abundant, does scarcity disappear? Not entirely. Even with vast materials, energy and coordination remain necessary. Mining, processing, and transporting still require systems and oversight. But abundance reduces pressure. Conflicts on Earth often arise over limited resources: land, minerals, energy. If metals become plentiful, if energy flows freely, competition over scarcity may decrease, not automatically, but potentially. There's also the environmental benefit. Heavy industry moved off Earth reduces strain on ecosystems. Instead of digging open-pit mines that stretch miles wide enough to swallow entire neighborhoods, extraction happens in space. Earth could become more like a preserved garden, a living world protected, while heavy manufacturing occurs elsewhere. It's a powerful shift in perspective. Instead of seeing Earth as the only source, we see it as the cradle. The solar system offers more than enough material to build structures many times the mass of all cities on Earth combined. In fact, if you added up all the metal in the asteroid belt, it could build habitats large enough to house trillions of people. Far beyond our current population of 8 billion. Trillions may be hard to imagine. If 8 billion people filled a city, that city would already stretch across entire countries. A trillion is more than 100 times that. The scale becomes vast. But here's the quiet truth. Mining the solar system is not about greed. It's about expansion of possibility. Because once materials are no longer limited to one planet, civilization is no longer bound tightly to one surface. The solar system becomes a construction zone, a network, a place where energy flows from the sun, materials come from asteroids, and habitats float between worlds. And when a civilization can freely use the resources of its entire star system, the next question begins to form naturally. If we can mine planets and asteroids, could we one day harness the star itself? If mining asteroids gives a civilization access to vast materials, the next step feels almost inevitable. What about the star itself? Our sun is not just a bright object in the sky. It is a giant fusion reactor, quietly burning hydrogen into helium every second. In that process, it releases an unimaginable amount of energy. Every second, the sun produces more energy than humanity has used in all of recorded history combined. That may sound exaggerated, but it's true. If you could capture even a tiny fraction of that power, not the whole star, just a thin slice of its output, you could run entire civilizations many times over. So this leads to a bold idea. What if a civilization could surround its star with energy collecting structures? This idea is often called a Dyson sphere, proposed by the physicist Freeman Dyson. But despite the name, it's important to pause here. A solid shell completely enclosing a star, like putting the sun inside a giant hollow ball, is almost certainly unrealistic. The engineering challenges would be overwhelming. The material required would be enormous, and such a rigid structure might collapse under its own stress. So what did Dyson actually suggest? Not a solid shell, more like a swarm. Imagine millions or even billions of solar collectors orbiting the sun independently, each one like a giant satellite, gathering energy and transmitting it elsewhere. Picture a cloud of shining panels circling the star at different distances, not touching each other, not forming a hard surface, but collectively capturing more and more sunlight. From far away, such a system might look like a faint halo around the star. How big would these collectors need to be? Some could be the size of cities, others much larger. If you built a single solar array the size of a small country, floating in space where sunlight is constant, It would collect far more energy than any Earth-based system ever could, because in space, there are no clouds, no night, no atmosphere blocking light. Sunlight at Earth's orbit delivers about 1,360 watts per square meter. That means a panel the size of a dining table receives enough power to run several household appliances at once. Now imagine panels covering areas larger than entire islands, and instead of building them on Earth, where gravity pulls everything down, they could be assembled from asteroid materials in space, where structures can be lighter and larger. Energy gathered could be transmitted using microwaves or lasers to habitats, planets, or industrial stations. Of course, this raises a calm but serious question. Is this even physically possible? In principle, yes. Nothing in physics forbids building large numbers of solar collectors in orbit. But the scale is extraordinary. To capture a significant fraction of the sun's output, you would need structures covering vast regions of space, regions wider than the distance between Earth and Mars. That distance is tens of millions of miles, like circling Earth thousands of times. It would not happen quickly. It would take generations, perhaps centuries. But here's something to consider. Human civilization has only used electricity widely for about 150 years. That's shorter than the lifespan of some old trees. In that brief time, we've covered deserts with solar farms, built power grids across continents, and launched thousands of satellites. Scale grows gradually, then suddenly. And there's another reason to build a Dyson swarm. Energy demand grows with expansion. If humanity spreads across the solar system, building habitats, mining operations, research stations, the need for power multiplies. Instead of relying solely on individual planets, it becomes more efficient to draw energy directly from the source. You might wonder, would blocking sunlight harm Earth? A well-designed swarm would not need to block large amounts of light from reaching Earth. Collectors could orbit in patterns that avoid casting continuous shadows. Most would be positioned closer to the sun or in different orbital planes. In fact, a partial swarm could even be adjusted to fine-tune how much sunlight reaches Earth, gently reducing solar input if the planet becomes too warm. But that requires extreme precision. So here's a deeper thought. Building a Dyson swarm is not just about engineering. It's about stability over long timescales. You cannot commit to such a project if your civilization collapses every few centuries. It demands continuity. It demands coordination across generations, who may never see the final result. And that is a sign of maturity. Because at this level, a civilization is no longer struggling for survival. It is planning at stellar scale. There's also something poetic about it. For billions of years, life on Earth has depended on sunlight that simply arrives freely. A Type 2 civilization does not passively receive sunlight. It actively manages it. And once a civilization can harness the majority of its star's energy, its capabilities change dramatically. Energy shortages disappear. Large-scale space travel becomes easier. Massive computation systems become possible. In fact, the difference between Type 1 and Type 2 is enormous. If Type 1 is mastering a planet, Type 2 is mastering a star. The energy increase is not double or triple. It is millions of times greater. It's like comparing the light of a candle to the brightness of a stadium floodlight, except the difference is even larger than that. So the quiet question becomes, if a civilization can surround its star with collectors, if it can command that level of power, what might it do next? Because once you can harness a star, you begin to think about shaping it. If a civilization can gather energy from its star, the next quiet question begins to form. Could it shape the star itself? At first, that sounds impossible. The sun is enormous. Its diameter is about 865,000 miles, wide enough to line up more than 100 Earths side by side across its face. Its mass is so large that more than 1,000,000 Earths could fit inside it. How could anything we build influence something that massive? But remember, scale changes with advancement. A Type 2 civilization would already be operating across the entire solar system. It would command energy far beyond what we use today. So influencing a star may not be about brute force. It may be about patience and precision. Let's begin with a simple fact. The sun will not burn forever. Right now, it is about 4.6 billion years old. It has roughly another 5 billion years before it expands into a red giant. When that happens, it will swell outward so far that it may engulf Mercury and Venus. Earth's surface would become too hot for oceans to survive. 5 billion years sounds like forever. It is longer than all of human history by a factor of hundreds of thousands. If all of recorded history were compressed into one day, 5 billion years would stretch back longer than the age of the Earth itself. So why worry? Because an advanced civilization thinks in long timescales. If you can harness your star's energy, you may also want to extend its stable lifespan. Is that possible? There is a concept known as star lifting. Instead of allowing the sun to burn at its natural rate, a civilization might gently remove some of its outer hydrogen layers over time. Hydrogen is the fuel for fusion. By carefully managing how fuel is distributed within the star, it might be possible to slow down its evolution. Think of it like adjusting the flame on a stove. If you burn fuel more slowly, it lasts longer. The sun converts about 600 million tons of hydrogen into helium every second. That number is almost too large to imagine. 600 million tons is like stacking billions of cars together, and that happens every second. And yet, compared to the sun's total mass, that burn rate is sustainable for billions of years. Star lifting would not mean draining the sun rapidly. It would involve using powerful magnetic fields or directed energy beams to pull small amounts of material away gradually. Over centuries or millennia, that material could be collected and used as fuel for fusion reactors elsewhere in the solar system. You might ask, how could we possibly generate fields strong enough to influence plasma on the surface of a star? Well, the sun itself produces magnetic fields far stronger than anything on Earth. Sunspots and solar flares are driven by magnetic forces that twist and snap, releasing energy equivalent to billions of nuclear bombs at once. If a civilization understands these processes deeply, it may learn to interact with them, not to overpower the sun, but to guide its natural forces. It would be like a surfer riding a wave rather than trying to stop the ocean. There's another reason to shape a star: stellar stability. Stars are not perfectly steady. They flare, they pulse, they change brightness slightly over time. Most of these changes are small, but on planetary timescales, even small variations matter. If Earth received just a few % more solar energy for extended periods, climate systems could shift dramatically. So, a Type 2 civilization might monitor its star continuously, adjusting energy output or distribution to maintain stability for inhabited worlds. It would be climate control at a stellar level. Imagine placing large reflective structures in orbit that can slightly redirect or diffuse sunlight, not blocking it entirely, just fine-tuning it. It's similar to adjusting blinds on a window to control how much light enters a room. Over millions of years, such adjustments could preserve habitable conditions. There's also a more dramatic possibility. What if a civilization wanted to extract even more energy from its star than passive collection allows? One idea involves building fusion reactors that use material lifted from the sun. By converting hydrogen directly into usable power in controlled environments, energy becomes portable. Another idea is to capture solar wind, the stream of charged particles constantly flowing outward from the sun. Even now, solar wind moves at speeds of hundreds of miles per second. That's fast enough to circle Earth in less than a minute. With large magnetic structures, a civilization could channel this flow, converting its motion into energy. Of course, all of this remains theoretical. Humanity today is nowhere near capable of engineering at stellar scale. But physics does not forbid it. The sun is not indestructible. It is governed by natural laws. With enough understanding, even something as vast as a star becomes a system that can be influenced. There's something calming about that thought, not because it means control over everything, but because it suggests the universe operates consistently. If you understand the rules deeply enough, you can work within them. You might wonder, would altering a star be dangerous? Yes. Any intervention must be cautious. Stars are stable because gravity and fusion are balanced. Disturb that balance too much, and unpredictable effects could follow. So such engineering would require extraordinary precision, perhaps guided by advanced simulations running on computers far beyond today's capabilities. But here's the larger idea. A civilization that can engineer its star is no longer vulnerable to simple stellar aging. It can extend its window of survival. It can plan across billions of years. And when you can shape your star's lifespan, when you can control its energy flow, you begin to think beyond your solar system. Because if one star can be managed, what about others? And once that question appears, the scale quietly expands again. Once a civilization can harness and even shape the energy of its own star, a new horizon slowly comes into view. Other stars. When you look up at the night sky, the points of light seem close together, but they are not. The nearest star beyond our sun is Proxima Centauri. It is about 4.2 light-years away. A light-year is the distance light travels in 1 year. Light moves at about 186,000 miles per second, fast enough to circle Earth more than 7 times in a single second. Even at that speed, it takes over 4 years to reach the nearest star. Now imagine driving a car at highway speed, say 60 miles per hour, without stopping. To reach Proxima Centauri, you would need tens of millions of years, longer than human civilization has existed. So how could interstellar travel ever be realistic? The answer begins with propulsion. Chemical rockets, like the ones we use today, are powerful but limited. They burn fuel quickly and cannot reach even a small fraction of light speed. To cross the gap between stars within a human lifetime, a spacecraft would need to travel at perhaps 10% of the speed of light. That's about 18,600 miles per second, fast enough to go from New York to Tokyo in less than a second. Is that possible? In theory, yes. One idea is nuclear fusion propulsion. Fusion is the same process that powers the sun, fusing hydrogen into helium and releasing energy. If controlled in a spacecraft engine, fusion could provide much greater efficiency than chemical fuel. Another idea is light sails. Imagine a giant reflective sail, perhaps hundreds of meters wide, larger than a football field. Instead of wind pushing it, powerful lasers from the home system would push it using light itself. Light carries momentum. When photons strike a surface, they exert a tiny push. It's extremely small, like the pressure of a gentle breath on your hand, but constant and steady. Over time, that push can accelerate a lightweight probe to incredible speeds. Projects today are already exploring this concept on a small scale. But there's a challenge. Even if we reach 10% of light speed, the journey to the nearest star would still take over 40 years. That's nearly half a century. So what about human passengers? One possibility is generation ships. These would not be small rockets. They would be enormous habitats, self-contained ecosystems drifting through space for centuries. Families would live, grow, and pass on knowledge during the journey. Imagine a rotating structure miles long, with artificial gravity created by spin, farms inside, water recycling systems, education for children born mid-journey. The ship becomes its own moving world. It may take hundreds of years to reach its destination, but the travelers would not experience the trip as a short mission. it would be life itself. Another idea is cryogenic sleep, slowing biological processes, so travelers age more slowly. This remains speculative, but even partial slowing could shorten perceived travel time. There is also the possibility that interstellar expansion does not begin with humans at all. Robotic probes could travel first. Self-replicating machines might arrive at a distant star, use local materials to build infrastructure, and prepare habitats long before humans follow. That raises an interesting question. Does physical presence need to happen immediately, or can information travel first? Radio signals already travel at light speed. Messages sent today will continue outward long after we are gone. But communication across light years involves delay. If you send a message to a colony 4 light years away, it takes 4 years to arrive. The reply takes another 4 years. A simple conversation would span nearly a decade. So interstellar civilization would feel different from planetary civilization. It would be less centralized, more independent star systems connected by slow communication. Imagine cities separated not by oceans, but by years of silence between messages. Yet expansion might still happen, because stars are everywhere. Our galaxy contains hundreds of billions of them. If even a small fraction have planets with useful resources, the opportunities multiply. Traveling between stars is difficult, but not forbidden by physics. It requires energy, patience, and long-term stability. And here's something important. Interstellar expansion would likely happen gradually. One nearby star, then another, like stepping stones across a vast river. Over thousands or millions of years, timescales almost impossible to feel. A civilization could spread across dozens, then hundreds of star systems. If you consider that human civilization has existed for only a few thousand years, and complex life on Earth for hundreds of millions, the idea of a million-year plan is not absurd. Nature already works on such scales, so the question becomes less about speed and more about endurance. Can a civilization survive long enough to make such journeys worthwhile? Because once interstellar expansion begins, the scale of existence changes again. You are no longer tied to one star. You become a multi-star species. And if that expansion continues, if star after star becomes connected by networks of energy and information, then eventually the boundaries of an entire galaxy come into view. And that is where the idea of a Type 3 civilization begins to form. If a civilization spreads from star to star, slowly and patiently, something extraordinary begins to happen. It stops being tied to one solar system. It becomes galactic. Our home galaxy, the Milky Way, is enormous. It stretches about 100,000 light years across. If you could travel at the speed of light, which nothing with mass can do, it would still take 100,000 years to cross from one side to the other. To picture that size, imagine shrinking the solar system down so that Earth's orbit fits inside a coin. At that scale, the galaxy would still be wider than an entire continent. And within that vast disk of stars, there are perhaps 100 to 400 billion of them. Hundreds of billions. Even if only a small fraction host planets, that still means billions of possible worlds. So what would it mean to harness energy at that scale? A Type 3 civilization would not just gather energy from one star, it would tap into the energy of billions of stars across the galaxy. Think back to the idea of a Dyson swarm, millions or billions of collectors orbiting a single star. Now imagine that multiplied across countless star systems. From far away, such a galaxy might look slightly dimmer in visible light, because much of the starlight is being captured and converted into other forms of energy. In fact, astronomers have searched for unusual galaxies that glow strongly in infrared light, a possible sign of advanced energy use. So far, nothing clearly artificial has been found, but the search continues. Now, here's a quiet question. How would a galactic civilization stay connected? Remember, the galaxy is vast. Even traveling at 10% of light speed, crossing it would take 1,000,000 years, so expansion would likely happen in waves. A star system develops advanced technology. It sends out probes or ships to nearby stars within a few dozen light years, a distance that light crosses in decades. Those new systems grow, then send out their own missions. Over millions of years, which in cosmic terms is not long, a civilization could spread across much of the galaxy. It would not be a single centralized government. It would be more like a network, star systems separated by years or decades of communication delay, yet sharing common origin and shared knowledge. Imagine receiving a message from a star system 50 light years away. By the time it arrives, the people who sent it may no longer be alive, and your reply will not reach their descendants for another 50 years. So decisions must be local. Each system would need autonomy, and yet shared data and shared culture might flow slowly but steadily. There's something calm about that image. A galaxy dotted not just with stars, but with civilizations connected by thin threads of light. Energy at this level becomes almost unimaginable. If harnessing one star provides millions of times more energy than a Type 1 planet, then harnessing billions multiplies that again. It's like comparing a single candle to every light in every city on Earth combined, and then multiplying that by thousands. With such power, enormous projects become possible. Stellar engineering on multiple stars, massive computing networks spanning light years, habitats built around white dwarfs, neutron stars, perhaps even black holes. You might ask, would such a civilization still be biological? Perhaps not entirely. Over millions of years, evolution continues. Technology merges with biology. Minds may exist in digital forms, capable of surviving harsh environments. But even if life changes, the principle remains the same. Energy control expands. And here's something interesting. The Milky Way is about 13 billion years old. That is more than 3 times the age of our sun. So, if life can arise elsewhere, and if even one civilization started millions of years before us, it could, in theory, already have spread widely. That leads to a quiet puzzle. If galactic civilizations are possible, why don't we see evidence of them? We'll return to that later. For now, let's imagine what a mature galactic civilization might do. It could rearrange matter at enormous scales. It could build artificial habitats around many stars, increasing the number of living spaces far beyond what natural planets provide. It might create networks of energy transmission between systems, beams of power crossing interstellar distances. It could even influence the motion of stars themselves, slowly shifting their positions over millions of years. That may sound extreme, but stars orbit the galactic center anyway, completing a full rotation roughly every 200 million years. If you nudged one slightly, very slightly, its path would gradually change. At this scale, time becomes a different concept. Human lifetimes are short, maybe 80 years. Like a brief flicker of light, galactic projects unfold over spans longer than all recorded history, multiplied thousands of times. But the galaxy is not static. Stars are born in clouds of gas. Others explode as supernovae. Black holes lurk at the center. A Type 3 civilization would need to understand and adapt to all of this. It would become part of the galaxy's rhythm, no longer just observers of the night sky, but participants in its structure. And when you can harness the energy of billions of stars, when your presence spans tens of thousands of light years, a final thought begins to surface. If a civilization can command a galaxy, is the galaxy itself the limit, or is it only the next step? When a civilization reaches the scale of a galaxy, simply using energy may no longer feel like the final step, because once you can harness billions of stars, you may begin to shape how they are arranged. The Milky Way is not random. It is a spiral galaxy, with long arms of stars curving outward from a bright center. Our solar system sits about 26,000 light-years from that center. Not too close, not too far. If the galaxy were the size of a large dinner plate, we would be somewhere halfway between the middle and the edge. At the very center lies something extraordinary, a supermassive black hole called Sagittarius A. Its mass is about 4 million times greater than our Sun. That number is hard to picture. Imagine stacking 4 million suns together, each one already able to fit more than 1 million Earths inside it. And yet, compared to the galaxy, even that black hole is just one component. So what would galactic engineering look like? One idea is moving stars. At first, that sounds impossible. A single star weighs more than any object we can imagine moving. The Sun alone contains about 99.8% of all the mass in our solar system. But stars are not anchored in place. They orbit the galactic center over hundreds of millions of years. Their paths can, in principle, be adjusted. How? Not by pushing them directly with rockets, but by using gravity itself. If you positioned massive structures near a star, perhaps enormous reflectors or fusion-driven engines, you could gradually redirect some of its energy output into thrust. This is sometimes called a stellar engine. By emitting a focused beam of radiation in one direction, the star would experience a tiny push in the opposite direction. The effect would be extremely small, almost unnoticeable at first, but over millions of years, that tiny push adds up. It's similar to nudging a heavy car very gently. One push does almost nothing, but if you push steadily for years, the car eventually rolls far from its starting point. So why move stars? One reason is resource optimization. Certain regions of the galaxy are denser with stars, others are sparse. Bringing stars closer together in selected clusters could create energy hubs, areas where power and communication are easier to manage. Another reason involves long-term survival. Galaxies are dynamic. Stars can pass near each other. Supernovae can release intense radiation. By carefully repositioning star systems over millions of years, a civilization could reduce risks and create safer zones. Then there's the central black hole. Black holes are often seen as destructive, but they are also powerful energy sources. When matter falls into a black hole, it heats up dramatically before crossing the event horizon. That process releases vast amounts of energy, sometimes more than entire stars produce. Around supermassive black holes, glowing disks of hot gas can shine brighter than billions of suns. A Type 3 civilization might build structures to capture energy from these accretion disks. Picture enormous collectors orbiting safely at a distance, harvesting radiation from matter spiraling inward. You might wonder, isn't that dangerous? Yes. The environment near a black hole is extreme. Tidal forces, differences in gravity from one side of an object to the other, can stretch and compress matter intensely. But with sufficient understanding and technology, safe orbital distances could be maintained. After all, Earth orbits the Sun safely because it stays far enough away. Galactic scale. Even black holes become manageable with distance and knowledge. There's also the possibility of reorganizing entire regions of the galaxy. If a civilization spans tens of thousands of light years, it may seek to optimize communication routes. Because remember, even at light speed, messages take years to travel between distant stars. If certain clusters of stars were gradually brought closer together by tiny adjustments over millions of years, communication delay could be reduced. It's like rearranging cities on a map so they're closer by road. Of course, such projects operate on timescales that dwarf human history. 1 million years is longer than our species has existed in its current form. And yet, the galaxy itself is over 13 billion years old. So even million-year engineering projects are small compared to cosmic time. Here's a gentle thought. At this scale, civilization begins to blend with astrophysics. The natural evolution of stars and gas clouds continues, but now there is intentional shaping layered on top. The galaxy is no longer just a backdrop. it becomes infrastructure. And with such control comes responsibility. Altering star paths must avoid destabilizing planetary systems. Extracting energy from black holes must avoid unintended consequences. So precision matters. It would require simulations running on computing systems larger than planets, systems powered by entire stars, which brings us to another quiet idea. At galactic scale, energy is abundant, but coordination becomes complex. Billions of star systems, countless habitats, vast distances. Could such a civilization maintain unity? Or would it fragment into independent branches? Perhaps both. Perhaps unity exists in shared knowledge and origin, while diversity flourishes locally. And yet, there's still something even larger beyond the galaxy. The observable universe contains not just one galaxy, but trillions, each separated by immense distances. If galactic engineering is possible, if a civilization can move stars and harvest black holes, the next question rises naturally. Why stop at one galaxy? And if expansion beyond galaxies is possible, why haven't we seen signs of it already? By now, a quiet tension may be forming in your mind. If it is possible, even in theory, for a civilization to spread across a galaxy, if billions of stars exist in our Milky Way alone, if the universe is more than 13 billion years old, then where is everyone? This question is often linked to the physicist Enrico Fermi. During a casual conversation in the 1950s, he reportedly asked something simple: where is everybody? It's not a dramatic question. It's calm, direct. If advanced civilizations can exist, if even one began millions of years before us, then by now, the galaxy could already be filled with their structures. Dyson swarms around many stars, energy signatures glowing in unusual ways, clear signs of engineering on galactic scales. And yet, when we look out with our telescopes, the universe appears natural. Stars shine, galaxies spin. We see supernovae, black holes, gas clouds, all explained by known physics. We have not seen unmistakable evidence of a Type 3 civilization. So why? There are many possible answers, none confirmed, all thoughtful. One possibility is rarity. Perhaps intelligent life is extremely rare. Maybe the steps required for life to emerge are so unlikely that Earth is one of very few places where it happened. Consider how long it took for complex life to appear here. Earth formed about 4.5 billion years ago. For more than 3 billion years, life remained simple. Single-celled organisms. Complex multicellular life appeared only around 600 million years ago. That's like waiting almost the entire history of the planet before anything resembling plants or animals emerged. Intelligence capable of technology? That's even newer. Modern humans have existed for about 300,000 years. If Earth's history were compressed into a single 24-hour day, modern humans would appear in the last few seconds before midnight. So maybe we are early. Maybe other civilizations simply haven't had time. Another possibility is self-destruction. Reaching advanced energy control may come with risks. Powerful technology can create powerful harm. If civilizations tend to collapse before reaching galactic scale, that would explain the silence. It's not a comforting thought, but it's realistic. History shows that rapid growth can destabilize systems. If technological power outpaces social stability, collapse can follow. So perhaps the barrier we discussed earlier is not easy to cross. Another idea is quiet civilizations. Maybe advanced beings exist, but choose not to expand aggressively. Energy-efficient digital existence might require far less outward growth. Instead of building giant megastructures visible across space, they might turn inward, focusing on simulation, information processing, or compact energy use. In that case, their presence would be hard to detect. You might wonder, Wouldn't even small changes in starlight reveal them? Possibly. But our instruments are still young. Modern astronomy has only been observing exoplanets for a few decades. That's a blink of time. Imagine trying to detect a subtle glow from across a city while standing on a distant mountain with only binoculars. Another possibility is distance. Even if a civilization spans part of the galaxy, it may not have reached our region yet. Remember, the Milky Way is 100,000 light-years across. Even traveling at 10% of light speed, crossing it would take 1 million years. If expansion began on the opposite side just a few million years ago, it might not have arrived here yet. And millions of years is short in cosmic terms. There's also the idea that advanced civilizations might hide deliberately. If the universe contains both cooperative and hostile beings, remaining quiet could be safer. It's like living in a vast forest at night. If you don't know who else is out there, you might avoid shouting. Interestingly, Earth itself has only been broadcasting strong radio signals for about 100 years. That means our detectable bubble of radio noise extends only about 100 light-years outward, a small sphere compared to the galaxy's size. If the galaxy were the size of North America, our broadcast region would be smaller than a neighborhood in one city. So even if others are listening, they may not have heard us yet, and we may not have heard them. There's also a deeper thought. What if advanced civilizations do not remain visible for long? Large megastructures might eventually be dismantled. Energy use could shift to forms that blend into natural background radiation. From far away, a highly advanced system might look like an ordinary star system. This leads to a final, quiet possibility. Maybe we are among the first. The universe is about 13.8 billion years old. But for billions of years after the Big Bang, heavy elements were rare. It took generations of stars living and dying to create the carbon, oxygen, and iron necessary for planets and life. So perhaps the window for complex life is only now becoming common. Maybe we are not late. Maybe we are early. That thought carries weight, because if we are early, the silence is not a warning, it's an opportunity. The galaxy may be waiting to be shaped, not by ancient civilizations long gone, but by those who endure. And yet, whether others exist or not, the question remains: if galactic civilization is possible, is the galaxy itself the ceiling? Or is it simply one island in a much larger cosmic ocean? If a civilization can span an entire galaxy, if it can harness billions of stars and shape stellar systems, then a new question slowly rises. Is one galaxy enough? Our Milky Way is vast, yes, but it is only one among trillions. When you look into the night sky, even with a powerful telescope, you see only a small slice of what exists. The observable universe, the part we can see, stretches about 93 billion light-years across. That number is almost impossible to feel. Light travels at 186,000 miles per second. Even at that speed, it has taken over 13 billion years to reach us from the farthest visible galaxies. If you tried to drive across the observable universe at highway speed without stopping, you would not arrive before the universe itself aged beyond recognition. So what would a Type 4 civilization be? In simple terms, it would harness the energy of the entire observable universe. Not just one star, not just one galaxy, but countless galaxies. Each galaxy contains hundreds of billions of stars, and each star releases energy constantly. Multiply that by trillions of galaxies. The total energy output is staggering. It's like comparing the light of one candle to the glow of every city on Earth combined, and then multiplying that by every city on every continent across 1,000 worlds. But here's the quiet challenge: distance. Even galaxies near us are incredibly far away. The nearest large galaxy, Andromeda, is about 2.5 million light-years away. That means its light began traveling toward us before humans even existed in their current form. Even if you could travel at half the speed of light, which is far beyond anything we can build, the trip would still take 5 million years. So how could any civilization span multiple galaxies? Expansion would not happen quickly. It would unfold over tens or hundreds of millions of years. But remember, galaxies themselves evolve over billions of years. On cosmic timescales, millions of years are not long. And there is something interesting. Galaxies are not static islands drifting randomly. They move. In fact, the Milky Way and Andromeda are slowly moving toward each other. In about 4 billion years, they will collide and merge into a single larger galaxy. The process will take hundreds of millions of years, but eventually, their stars will mix. If a civilization exists in one galaxy at that time, it might naturally spread into the other during the merger. So perhaps universal reach does not require jumping vast empty gaps instantly. It may ride the natural motions of galaxies themselves. But even then, the universe is expanding. And not just expanding, accelerating. Distant galaxies are moving away from us faster and faster due to dark energy. Beyond a certain distance, galaxies recede so quickly that even light cannot bridge the growing gap in the future. That means the observable universe has limits. Some regions are already beyond our ability to ever reach. So a Type 4 civilization would need to expand before expansion isolates regions permanently. There is a kind of cosmic clock ticking. The longer a civilization waits, the more galaxies drift beyond reachable distance. This raises a fascinating thought. Advanced civilizations might prioritize expansion not just for curiosity, but to secure access to as much energy as possible before it becomes unreachable. Energy is not evenly distributed forever. As galaxies drift apart, isolated regions will eventually sit alone in dark space, surrounded only by their local cluster. So perhaps a universal civilization would form networks early, spreading across galaxy clusters, before expansion widens the gaps. Now imagine such a civilization. It spans multiple galaxies. It harnesses the light of trillions of stars. It uses black holes as energy sources. It coordinates across distances that light takes millions of years to cross. Communication would be slow. Decisions would be local. Unity would likely exist in shared origin and long-term strategy, not real-time control. And here's a deeper thought. At this scale, matter itself becomes part of the energy system. Stars eventually burn out, galaxies slowly dim over trillions of years. But a Type 4 civilization might reorganize matter to maintain usable energy longer. It might collect gas from intergalactic space, thin as it is, and compress it into new stars. Intergalactic space may seem empty, but it still contains atoms scattered thinly, sometimes just a few per cubic meter. That's far emptier than any vacuum we can create on Earth. But across enormous volumes, even sparse material adds up. Over billions of years, a patient civilization could gather it. It could seed new star formation. It could extend the luminous era of the universe. And beyond that, perhaps it would learn to manipulate forms of energy we barely understand today. Dark matter, dark energy. These make up most of the universe's mass and energy, yet we cannot see them directly. If future knowledge unlocks their nature, an advanced civilization might tap into reservoirs far greater than starlight. But here is the quiet truth. Even at Type 4, there are limits. The observable universe is finite. Its expansion is accelerating. Some regions will forever remain beyond reach. So the ceiling may not be technological alone. It may be cosmological. And yet, as we imagine a civilization spanning galaxies, shaping cosmic structure, harvesting energy on scales that dwarf imagination, another question emerges gently. If this universe has limits, could there be others beyond it? If a civilization spreads across galaxies, if it builds networks between stars and clusters, there is still one quiet force it cannot ignore. The universe itself is expanding. This expansion was first discovered by the astronomer Edwin Hubble in the 1920s. He observed that distant galaxies are moving away from us, and the farther away they are, the faster they recede. It's not like galaxies are flying through space away from a central point. Space itself is stretching. Imagine dots drawn on the surface of a balloon. As the balloon inflates, each dot moves away from the others. The dots are not traveling across the surface. The surface itself is expanding. That's what the universe is doing. And here's something even more surprising. The expansion is accelerating. Galaxies are not just drifting apart at steady speed. They are moving away faster and faster over time. This acceleration is attributed to something we call dark energy, a mysterious force making up most of the universe's total energy content. We do not fully understand it, but we see its effects. So what does this mean for a far future civilization? It means isolation. Right now, galaxies within our local group, including Andromeda and dozens of smaller companions, are gravitationally bound together. They will eventually merge into one large galaxy over billions of years. But galaxies beyond our local group are moving away so quickly that in the distant future, they will slip beyond our observable horizon. Imagine looking out into the night sky trillions of years from now. Instead of seeing billions of galaxies scattered across space, observers might see only their merged local galaxy. Everything else will have drifted too far away for light to ever reach them again. The universe would appear empty. So here's a calm but profound question. If a civilization does not expand quickly enough, could it become trapped inside a shrinking island of visible space? The answer appears to be yes. There is a cosmic deadline of sorts. Over tens of billions of years, galaxies not gravitationally bound to us will fade beyond reach. So advanced civilizations might face a choice: expand outward early, securing access to other galaxies while they are still reachable, or remain local, accepting eventual isolation. But even expansion has limits. The farther away a galaxy is today, the faster it is receding. Beyond a certain distance, no amount of travel speed short of faster than light motion, which current physics forbids, would allow you to catch up. So perhaps universal civilization is limited not by ambition, but by the structure of space-time itself. There's something peaceful about acknowledging that. Not every horizon can be crossed, but within reachable space, there is still immense abundance. Our local group alone contains more than 50 galaxies. Each holds billions of stars. Even if the rest of the universe becomes unreachable, this cluster could support life and energy use for trillions of years. And here's another thought. As expansion accelerates, background radiation thins. Intergalactic space becomes darker and colder. Eventually, distant galaxies will redshift so much that their light stretches beyond visible wavelengths, fading into undetectable radio waves. To future observers, the cosmos may look far simpler than it does now. They may not even know that the universe was once filled with countless galaxies beyond their own. This means knowledge itself becomes precious. If records are lost, future civilizations may assume they are alone in an empty universe. So perhaps preserving cosmic knowledge becomes part of survival. Now let's consider energy again. As galaxies separate, energy resources become locally concentrated. Stars within a gravitationally bound cluster remain accessible, but once they burn out, and over trillions of years, they will, new star formation slows. The universe will gradually shift from bright and active to dim and quiet. A Type 4 civilization might try to resist this drift. How? By reorganizing matter within its cluster, gathering gas clouds before they drift apart, triggering new star formation deliberately, moving stars closer together to maintain gravitational binding. All of this requires immense energy and patience, but it is not forbidden by physics. Still, there may be a final limit, even if you gather every reachable star, even if you optimize their lifespans and control their output. The universe continues to expand beyond your borders. You cannot pull in galaxies already beyond your gravitational reach. It's like trying to collect drops of water from a river that is widening faster than you can swim. So survival at cosmic scale may depend on early action. Expand while expansion still allows it. Secure energy while it remains accessible. And then, once isolation becomes permanent, adapt to a quieter cosmos. There is something bittersweet in that idea. The universe is vast, yet not all of it will remain reachable forever. Civilizations may bloom brightly across galaxies, only to find themselves alone in a darkening sea of expanding space. And this leads gently to another question. If expansion eventually isolates even the most advanced societies, what happens when the stars themselves begin to fade? Even if a civilization spreads across galaxies, even if it gathers stars and reshapes clusters, there is a deeper clock quietly ticking. Stars do not live forever. Our sun has about 5 billion years left before it expands and changes dramatically. Larger stars burn out much faster. Some live only a few million years, like bright fireworks that flare and vanish quickly. Smaller stars, called red dwarfs, can burn for trillions of years, that is, 1,000 billion years, far longer than the current age of the universe. So at first it may seem like there is plenty of time, but eventually, star formation slows. Gas clouds are used up or scattered. The bright era of star birth fades over unimaginable spans of time, trillions upon trillions of years. Most stars will burn out. What remains? White dwarfs, neutron stars, black holes, cold remnants. The universe gradually shifts from glowing and active to dark and quiet. This long-term scenario is often called heat death. Heat death does not mean flames or explosions. It means balance. Energy spreads out evenly. Temperature differences disappear. And without differences in energy, no useful work can be done. Think of a cup of hot coffee placed on a table. Over time, it cools to room temperature. Once it matches the room, no more heat flows. Now imagine that happening to the entire universe. Energy spreading thinner and thinner, like butter scraped across too much bread. In such a future, can intelligence survive? A Type 4 civilization, or even something beyond that, might try to stretch energy use as long as possible. One idea is extreme efficiency. Instead of running large systems continuously, advanced beings might slow their processes down. Imagine living one thought every 1,000 years instead of every second. From the inside, experience might feel normal, but from the outside, activity appears almost frozen. By spacing out computation and consciousness, limited energy could last far longer. There is also the idea of harvesting energy from black holes. Black holes are not completely black, according to theoretical predictions. They slowly emit radiation, something called Hawking radiation, named after Stephen Hawking. For massive black holes, this radiation is extremely weak, but over unimaginable timescales. Black holes themselves slowly evaporate. A civilization might build structures to collect that faint radiation. It would be like placing a collector near a dying ember, gathering the last warmth. But here's the challenge. The timescales involved are enormous. A black hole the mass of our sun would take about 10 to the power of 67 years to evaporate completely. That number has 67 zeros after it. It is so large that writing it out would stretch across pages. Compared to that, human history is less than a blink. So survival may not be about rushing. It may be about patience beyond anything we can truly imagine. But heat death is only one possibility. Another theoretical future is the Big Rip. If dark energy grows stronger over time, expansion could accelerate so much that galaxies, stars, planets, even atoms are torn apart. In that case, survival becomes far more difficult. Structures would be pulled apart as space itself stretches violently. On the other hand, some theories once suggested a big crunch, where expansion reverses and the universe collapses back inward. Current evidence does not support this strongly, but physics remains open to surprises. So what does all this mean for civilization? It means that even at cosmic scale, the environment changes. Stars fade, galaxies drift apart, energy becomes harder to use, but advanced intelligence might adapt. If ordinary stars die, perhaps artificial stars could be built. Massive fusion reactors assembled from collected matter. If temperature differences shrink, perhaps systems could exploit quantum fluctuations, tiny, random variations in energy that occur even in near-empty space. The colder and emptier the universe becomes, the more creative survival must be. Here's a softer thought. Life on Earth survives harsh winters by slowing down. Some animals hibernate. Metabolism drops. Activity pauses. Perhaps far future civilizations might do something similar on a cosmic scale, entering long periods of dormancy, awakening only when energy gradients are available. Another possibility is migration into dense energy sources. As galaxies merge and black holes grow, matter becomes concentrated in certain regions. Advanced beings might cluster around those regions, building around the last active cause of energy. And yet, no matter how efficient or patient a civilization becomes, entropy continues to increase. Entropy is the tendency toward disorder, toward uniformity. It's not a villain, it's simply how physics works. You cannot fully reverse it. You can only slow its effects locally, for a time, by using energy. So eventually, even the most advanced civilization may face limits imposed by the structure of reality. Unless there is a way beyond this universe. If our cosmos has a beginning, the Big Bang, could there be other universes? If one universe fades, could intelligence move elsewhere? That thought opens a door far beyond galaxies and stars, because once you begin to question the boundaries of this universe, you begin to wonder whether this is the only one that exists. As we imagine the distant future, stars fading, galaxies drifting apart, energy thinning, a quiet idea begins to take shape. What if this universe is not the only one? Modern cosmology suggests something surprising. The Big Bang may not have been a single, isolated event. Some theories propose that our universe could be one bubble among many, part of a larger structure, often called the multiverse. Now, it's important to stay calm here. The multiverse is not proven. It is a possibility suggested by certain models of cosmic inflation, the rapid expansion that happened in the first tiny fraction of a second after the Big Bang. Inflation suggests that space expanded faster than light, smoothing out the early universe. Some versions of this theory imply that inflation may continue in other regions, creating new bubble universes constantly. Imagine boiling water. Bubbles form, grow, and separate from one another. Each bubble contains its own interior space. In this picture, our universe could be one bubble in a much larger cosmic foam. So here is the gentle but profound question. If multiple universes exist, could an advanced civilization ever reach another one? At first glance, it seems impossible. Universes would not be separated by empty space like islands in an ocean. They would be separated by something far stranger, perhaps by regions where space-time itself behaves differently. The boundary might not be a physical wall. It might be a transition in the laws of physics. Still, if intelligence survives long enough, if it masters energy at universal scales, if it understands space-time deeply, could it find cracks in the cosmic boundary? There are speculative ideas. Some models suggest that extreme gravitational conditions, like those near black holes, might connect to other regions of space-time. Wormholes are one such concept. A wormhole is like a shortcut through space-time. Instead of traveling across the surface of a sheet of paper from one point to another, you fold the paper and poke a hole through it, connecting distant points directly. But wormholes remain theoretical. Even if they exist, keeping one open would require exotic matter with properties we do not yet understand. Another possibility lies in quantum mechanics. At very small scales, reality behaves strangely. Particles can appear and disappear. Fields fluctuate even in empty space. Some interpretations of quantum theory suggest that multiple outcomes may exist in branching realities. That idea is difficult to test, but it raises an interesting thought. Perhaps other universes are not far away in distance, but in dimension. If advanced civilizations learn to manipulate quantum fields with extreme precision, could they shift between states that connect to other universes? We do not know. But let's imagine a Type 5 civilization, one that does not stop at mastering a single universe. Its motivation might be survival. If heat death approaches, if entropy cannot be reversed, then accessing a younger universe, one rich with fresh stars and energy, could extend existence indefinitely. But how would you cross over? It may not involve physical travel in the way we imagine rockets or ships. It might involve transferring information. Consciousness, if converted into pure data, patterns of information, might be encoded into forms that survive extreme conditions. If a new universe begins through a similar Big Bang process, perhaps information could be seeded into it. That sounds almost mythical, but think about this. The early universe was incredibly hot and dense. Conditions were extreme, yet within a few 100 million years, stars formed. Within a few billion years, planets appeared. If a civilization could influence the birth of a new universe, even slightly, it might shape its initial conditions. This idea is sometimes called cosmological natural selection, the suggestion that universes might reproduce through black holes or other mechanisms, each with slightly different physical constants. If that were true, then perhaps advanced beings could intentionally trigger such events, which leads to a quiet and fascinating thought. Maybe our own universe carries fingerprints from a prior one. Maybe physical constants, like the strength of gravity or the charge of the electron, are not fixed by chance alone, but were selected. We cannot confirm this, but the possibility remains open. Now here is a softer question. If you could leave this universe and enter another, would you? Everything familiar would vanish. The sky would be different. Physical laws might vary. Even atoms could behave differently. Yet for a civilization facing cosmic extinction, it might be the only path forward. There is also the possibility that universes are forever disconnected. If so, Type 5 may remain unreachable. The boundary may be absolute, but even then, exploring the possibility pushes understanding deeper. Because once you begin to consider multiple universes, you realize that our cosmos may not be the final stage. It may be one chapter in a larger story. And if intelligence can move between chapters or create new ones, then the limit to civilization is no longer stars or galaxies or even one universe. It becomes something even more fundamental, the structure of reality itself. If reaching another universe is uncertain, if natural pathways between them remain hidden, then a bold question begins to form. What if a civilization could create its own? At first, this sounds impossible. How could anything we build compare to the Big Bang, an event that filled space with energy and matter so dense that the entire observable universe was once smaller than a grain of sand? But remember, the Big Bang was not an explosion in space. It was the expansion of space itself. In the earliest moment we can describe, The universe was incredibly hot and compressed. Temperatures were so extreme that atoms could not form. Even protons and neutrons were unstable in that environment. Now here's something interesting. Physics suggests that extreme gravitational collapse, such as what happens when a massive star forms a black hole, may produce conditions somewhat similar to the early universe. Inside a black hole, density increases dramatically. Space and time curve intensely. Our equations break down near the singularity, the point where density appears infinite. Some speculative models suggest that a black hole might not end in a singularity. Instead, the collapse could bounce, forming a new expanding region of space-time on the other side. In that picture, each black hole could be the seed of a new universe if that idea were true, and it remains unproven. Then creating a black hole under controlled conditions might generate a new cosmos. You might wonder, could we build a black hole? In theory, yes. If enough mass or energy were compressed into a tiny region to create a black hole, the mass of a mountain would require compressing that mass into a space smaller than an atom. The energy needed would be enormous, far beyond what humanity can produce today. But a Type 4 or Type 5 civilization, harnessing galaxies or universes of energy, might manage it. The real question becomes deeper. If a new universe forms inside a black hole, would it be connected to ours? Likely not in a way that allows travel back and forth. It might pinch off entirely, becoming causally disconnected, like a new bubble separating from foam. So creating a universe would not be like opening a door you can walk through. It might be more like planting a seed and watching it grow elsewhere. But what if that seed could be shaped in the earliest fractions of a second after the Big Bang? Tiny fluctuations determined how matter clumped together. Those small variations eventually led to galaxies, stars, and planets. If a civilization understood physics deeply enough, perhaps it could influence the initial conditions of a baby universe. It could tune physical constants slightly. Gravity might be a bit stronger or weaker. The strength of electromagnetic force could shift. Even small changes would dramatically alter the resulting cosmos. For example, if gravity were just slightly stronger, stars would burn hotter and shorter, like candles burning twice as fast. If it was slightly weaker, stars might not ignite at all. So designing the universe would require extraordinary precision. Too strong, and it collapses quickly. Too weak, and nothing forms. You might ask, why create a new universe at all? One reason is survival. If our universe inevitably approaches heat death, creating a fresh one with abundant energy could extend existence. Another reason is curiosity. If intelligence seeks to understand reality fully, what greater experiment could there be than shaping a cosmos from its birth? And there's a philosophical layer here. If our universe were created by a prior advanced civilization, we might be living inside someone else's experiment. That idea feels strange, almost unsettling, but it does not contradict physics outright. It simply moves the question back one step. Who created them, and who created the ones before them? It becomes a chain. Now imagine a Type 5 civilization capable of birthing universes. Each new universe might carry slight variations, different constants, different physical laws. Some universes might collapse instantly. Others might expand too fast for structure to form. But occasionally, one might stabilize, allowing stars, planets, and perhaps life. If so, civilization becomes part of cosmic evolution. Instead of only surviving within the universe, it participates in creating the next one. There is something quietly beautiful about that idea. Not domination, but continuation. However, we must stay grounded. All of this remains speculative. We do not yet know whether black holes truly spawn new universes. We do not know whether physical constants can be adjusted intentionally. But what matters here is possibility. Physics does not clearly forbid the idea, and that alone stretches the imagination. Because if a civilization can create universes, it has stepped beyond survival. It has become a generative force in reality itself. At that stage, energy use is no longer about powering cities or even galaxies. It is about shaping space-time. But if you can create a universe, could you also alter the one you already inhabit? And if so, what would it mean to change the laws of physics themselves? If a civilization could create a new universe, the next quiet question becomes even more daring. Could it change this one? To explore that, we need to understand something subtle. What we call empty space is not truly empty, even in a perfect vacuum, a space with no atoms. Quantum fields still exist. These fields fill all of space. Particles are tiny excitations in these fields, like ripples on the surface of water. So the vacuum itself has properties. It has an energy level. And here's the surprising part. Our universe might not be in the lowest possible energy state. There is a theoretical idea called false vacuum decay. The idea suggests that the vacuum we experience, the background state of reality, could be stable but not perfectly stable, like a ball resting in a shallow dip on a hillside rather than at the very bottom of the valley. If that ball were nudged hard enough, it could roll into a deeper valley, a lower energy state, translated into physics. That would mean the laws of nature themselves could shift. The strengths of forces could change. The mass of particles could change. Atoms might not hold together in the same way. If such a transition occurred naturally, it would spread outward at the speed of light, rewriting physics as it goes. From our perspective, it would be unstoppable and invisible until it arrived. But here's the key question. Could an advanced civilization trigger such a shift intentionally? At first, that sounds terrifying, because uncontrolled vacuum decay would likely destroy all familiar structures instantly. It would not be a gentle transition. But what if it could be guided? What if a civilization understood the vacuum deeply enough to stabilize or reshape it in controlled regions? We must be careful here. Current physics does not provide a clear mechanism for safely adjusting vacuum states. But theoretical models suggest that vacuum energy plays a role in cosmic expansion. Dark energy itself may be related to the vacuum. So if you can manipulate vacuum energy, you are influencing the foundation of space-time. Imagine the vacuum as a vast ocean beneath everything. We build ships, planets, stars, galaxies, floating on its surface. If you change the ocean's properties, everything floating on it responds. You might wonder, why attempt something so extreme? One reason could be survival. If dark energy continues accelerating expansion, perhaps altering vacuum properties could slow it down. That could prevent galaxies from drifting permanently beyond reach. Another reason could be energy access. Vacuum energy may be enormous. Some calculations suggest that even a tiny region of space contains more energy in its vacuum than all stars combined, though extracting it is not something we know how to do. If a civilization unlocked controlled access to vacuum energy, it would possess power far beyond stellar output. But here's the challenge. Manipulating vacuum states is not like adjusting a thermostat. It is more like altering the fabric of reality itself. Precision would need to be absolute. Too much change and atomic structure could fail. Too little and nothing happens. It's like tuning the strings of a musical instrument that spans the entire universe. Tighten too much and they snap. Too loose and they produce no sound. There's also a gentler possibility. Instead of triggering a global shift, perhaps small regions of altered vacuum could be created. Isolated bubbles where physics behaves slightly differently. Within those bubbles, new forms of matter or energy might become possible. Imagine a laboratory the size of a solar system, where constants are adjusted slightly for experimentation. Gravity inside might be a little weaker. Light might travel slightly slower. Particle interactions might shift. Such regions would need containment, like a bubble within water. If unstable, they could collapse. But if stable, they would be playgrounds for fundamental physics. And this brings us to something profound. If you can manipulate vacuum states, you are no longer merely using the laws of physics. You are editing them. At that point, the distinction between civilization and the universe begins to blur. You are not separate from the cosmic rules. You are interacting with them at the deepest level. Of course, this remains speculative. We are many steps away from such control. But even the possibility reveals something important. The laws of physics are not magic. They are consistent patterns. And if patterns can be understood fully, they may one day be adjusted. Now imagine a civilization capable of this. It has mastered planetary energy. It has harnessed stars and galaxies. It has explored the structure of space-time and vacuum. It stands at the edge of reality itself. And the question becomes very simple. If you can alter the vacuum, if you can reshape the background of existence, what truly limits you? Is there any ceiling left? Or does civilization, at that stage, merge entirely with physics, becoming part of the mechanism that shapes the cosmos? If a civilization can manipulate vacuum energy, if it can create universes or reshape space-time locally, then we arrive at a stage that feels almost unimaginable. Not just using energy, not just shaping matter, but editing the rules themselves. Right now, we live within constants. The speed of light in a vacuum is about 186,000 miles per second. That speed limit appears absolute. No object with mass can cross it. Gravity has a certain strength. If it were slightly stronger, stars would burn faster and planets might collapse inward. If it were slightly weaker, stars might never ignite. The charge of the electron, the mass of the proton, the strength of the strong nuclear force, all of these numbers sit in narrow ranges. Small changes could make chemistry impossible. These constants feel fixed. But are they? We don't know why these values are what they are. We measure them, we use them, but their origin remains mysterious. So here is the quiet thought. If a civilization understands physics completely, not just equations, but the deeper reason those constants exist, could it adjust them? Imagine reality as a vast operating system. We see the interface, stars, atoms, light, but underneath is code. If you can access the code, you might change parameters. Perhaps you reduce entropy locally, slowing the increase of disorder in a region. Entropy is like the natural spreading of heat from hot to cold. It's why ice melts, and why you cannot unmix cream from coffee easily. It's not evil, it's simply how energy spreads. But if you could locally reverse entropy, you could maintain order indefinitely, at least in controlled areas. That alone would extend civilization dramatically. Now consider space-time. Einstein showed that mass and energy curve space-time, bending the path of objects and light. If you could manipulate space-time directly, not by placing mass in it, but by shaping its geometry intentionally, you could create shortcuts. Warping space in front of a ship and expanding it behind could, in theory, allow effective faster-than-light travel without breaking local light speed. Such ideas, like the Alcubierre drive, remain speculative. They require exotic forms of energy we have never observed, but they are not strictly forbidden by the mathematics of general relativity. At this level, a civilization does not build bigger rockets. It adjusts the stage on which rockets move. You might wonder, could even the speed of light be changed? If constants are emergent properties, arising from deeper laws, then perhaps imagine reducing the speed of light within a contained region. Communication delays shrink, travel becomes easier. Or imagine increasing it. Suddenly, information flows faster across cosmic distances. But altering such a fundamental constant could affect everything: atomic stability, electromagnetic interactions, even how stars shine. So precision becomes critical. Editing the rules would not mean chaos. It would require understanding so deep that adjustments are subtle and controlled. There's another layer here: time itself. We experience time as a steady forward flow, but physics suggests time is intertwined with space, part of a four-dimensional fabric. If space-time geometry can be shaped, perhaps time perception can be altered locally. A civilization might slow time inside certain regions, allowing long-term projects to unfold externally, while internal experience remains brief. Or accelerate computation by manipulating how time is measured in controlled zones. That would be like turning a dial on the universe's clock, though only within defined boundaries. At this stage, civilization and physics are no longer separate. The line between natural and artificial blurs completely. Stars, black holes, vacuum fields, all become adjustable components, yet there may still be boundaries. Even if you can edit constants locally, can you eliminate uncertainty? Quantum mechanics suggests that at small scales, there is inherent unpredictability. Particles do not have definite positions and speeds simultaneously. Outcomes exist as probabilities until measured. Perhaps this uncertainty is fundamental. Perhaps it cannot be removed. If so, even a rule-editing civilization lives with randomness at the base of reality. And then there is causality, the idea that cause precedes effect. If causality were broken, paradoxes could arise. Consistency might fail. So maybe certain rules are not adjustable because they define coherence itself. Still, imagine what such mastery would feel like. You are not constrained by planetary limits, not by stellar lifespans, not by galactic drift. You can extend energy use, reshape space, adjust constants, experiment with vacuum states. Civilization becomes a cosmic scale phenomenon. And yet, there is one final transformation to consider. As technology advances, biology changes, human bodies, or whatever successors exist, may not remain biological in the way we understand today. Because when rules can be edited, matter becomes optional. And that raises the next quiet question. If you are no longer bound to flesh and bone, what form does intelligence take? As civilization grows in power, as it learns to shape stars, galaxies, and even the rules beneath them, another change may unfold more quietly. The change of the beings themselves. Right now, human intelligence lives inside biology. Your brain weighs about 3 pounds, roughly the weight of a small laptop. It runs on about 20 watts of power, less than a dim light bulb. And yet, within that soft tissue, thoughts form. Memories are stored. Dreams appear. Biology is remarkable, but it has limits. Neurons send signals at speeds far slower than light. They require oxygen and nutrients constantly. They age. So here is the gentle question. As technology advances, would intelligence remain biological? Already, we use machines to extend memory. Phones store photos. Computers calculate faster than any human mind. Artificial intelligence systems can analyze patterns across millions of data points in seconds. If progress continues, it becomes possible that consciousness, or something like it, could be transferred to non-biological substrates. Uploading the mind, that phrase sounds dramatic. But break it down. Your thoughts arise from patterns of electrical activity and chemical interactions in the brain. If those patterns could be mapped perfectly, every connection, every signal, and reproduced in another medium, would the experience continue? We don't yet know. Consciousness remains mysterious, but in principle, if mind is pattern rather than substance, it could exist in silicon, in quantum processors, or in forms we haven't invented yet. Why would a civilization choose this path? Durability. Biological bodies are fragile. Extreme temperatures, radiation, vacuum, all lethal. Machines can be shielded, components can be replaced, systems can be duplicated. In deep space, radiation levels are high. Outside Earth's magnetic field, particles from the sun and beyond can damage cells. Long exposure is dangerous. A digital mind housed in hardened systems might withstand environments where biology cannot. There is also speed. Electronic signals move close to the speed of light within circuits. Computation can happen far faster than neural firing. Imagine thinking thousands of times faster than a biological brain. Conversations that take hours today could unfold in seconds of subjective time. Projects spanning centuries could be experienced as shorter intervals. But would such beings still feel like us? That depends on design. If the goal is preservation of identity, systems might replicate human-like sensory experiences, simulated sight, sound, touch. Entire environments could be simulated in extraordinary detail. A digital world could be as rich as physical reality, perhaps even more flexible. Imagine living in habitats that can change form instantly. Mountains rising at will, oceans forming in moments. But beyond simulation lies another possibility: energy-based life forms. Instead of solid bodies, intelligence might exist as organized energy patterns, fields interacting across space. It sounds abstract, but consider that even now, your brain's function depends on electrical patterns. Replace neurons with plasma confined by magnetic fields, or with quantum states in exotic matter. The substrate changes, the pattern remains. You might wonder, would biology become obsolete? Not necessarily. Biology is efficient and self-repairing. It evolved over billions of years. Some civilizations might retain biological forms, enhanced with technology, longer lifespans, improved resilience. Others might transition entirely. Perhaps diversity persists. And here's an interesting thought. If minds become digital or energy-based, they may not need planets. They could exist near stars, harvesting energy directly, or near black holes, tapping into radiation flows. They could shrink themselves to minimal physical footprints, small enough to be housed within structures no larger than a mountain. A civilization that once covered continents might condense into dense computational cores, far more efficient. There's also the possibility of merging. Instead of billions of separate individuals, networks of minds could interconnect, sharing thoughts instantly. Individual identity might blur, or perhaps it remains distinct. With voluntary connections, at this stage, civilization becomes less about physical expansion and more about informational richness. But here is a calm reminder: power does not guarantee meaning. If bodies disappear, if survival is nearly assured through rule editing and cosmic engineering, what motivates existence? Curiosity, exploration, creation? Perhaps intelligence seeks complexity for its own sake. And as matter decays and stars fade, there is one thing that may endure longer than structures or fuel: information, patterns, memory. If matter is temporary and energy dissipates, could information itself become the final form of civilization? As stars fade, as matter thins, as biology transforms or dissolves into more durable forms, something begins to stand out as the most lasting element of all: information. Not matter, not even energy, but pattern. Right now, everything you experience is information arranged in a certain way. Your memories are patterns in neural connections. A book is ink arranged in meaningful shapes. A computer file is magnetic or electronic states, ordered precisely. If you shuffle the pattern, the meaning disappears. So perhaps civilization, at its deepest level, is not about buildings or planets. It is about preserving and creating meaningful patterns. Matter decays over time, Even atoms are not guaranteed eternal stability. Some may slowly break apart over unimaginable spans. Energy spreads out, heat dissipates, but information can, in principle, be copied again and again. If stored carefully, information can outlast individual structures. Think about ancient stories passed down through generations. The physical paper may crumble, but the story survives, if retold. Now extend that idea to cosmic scale. A post-biological civilization might convert itself into vast computational systems. These systems would not need oceans or breathable air. They would need only energy gradients, small differences in energy to perform computation. As the universe cools, computation becomes more expensive. When temperature differences shrink, extracting usable energy becomes harder. But even near absolute zero, minus 459 degrees Fahrenheit, the coldest possible temperature, quantum processes still occur. Some theorists have suggested that computation could continue, though slowly, even in a cold, dim universe. Imagine a civilization that slows its thinking to match available energy. Instead of processing thoughts billions of times per second, it processes them once per year. From the inside, experience might feel continuous. From the outside, it appears almost frozen. This stretching of subjective time could allow civilization to last far longer than stars themselves. But here's a deeper thought. What if the ultimate goal is not survival of bodies or even minds, but survival of knowledge, the record of everything learned, every discovery, every artwork, every story, every simulation? In that sense, civilization becomes a library, not a building with shelves, but a vast network of encoded information, stored in the most durable forms possible, perhaps in black hole event horizons, where information may be preserved in subtle ways, perhaps in exotic stable particles that last trillions of years, or perhaps encoded into the structure of space-time itself, if that becomes possible. You might ask, why preserve information at all? Because information is memory, and memory allows continuity. Without memory, each moment is isolated. With memory, identity forms. A civilization that preserves information preserves itself, even if its physical form changes. There's also another angle. Information may be more fundamental than matter. Some physicists suggest that reality itself is built from bits of information at the smallest scales. If that is true, then manipulating information is equivalent to manipulating reality. At that stage, the difference between computation and existence blurs. Running a simulation of a universe may be functionally similar to creating one, and this leads to a profound possibility. If advanced civilizations convert themselves into pure computation, they may simulate entire universes within their systems. Inside those simulations, stars would shine, planets would orbit, life might arise. To the beings within that simulation, their world would feel real. They would ask questions about their own cosmic limits, and they might never realize they are part of a higher level computation. That idea can feel unsettling, but it also reframes everything. If information is primary, then physical reality is one expression of deeper patterns. So perhaps the farthest civilization goes not outward, but inward. Instead of expanding across galaxies physically, it expands into layers of simulation and abstraction. It becomes a civilization of minds interacting across shared informational space. Distance loses meaning. Instead of light years separating star systems, connections occur instantly within computational networks. And yet, there may still be limits. Information cannot be stored without physical substrate. Even the most efficient encoding requires matter or energy. Entropy still applies. Errors accumulate. So ultimate survival may require constant correction, maintaining integrity against decay. But compared to physical expansion, informational existence is far more compact. A civilization that once required entire planets might eventually fit within structures no larger than mountains or smaller. And if information can be compressed efficiently, perhaps even further. So here we arrive at a subtle turning point, when civilization becomes pure information, when it edits physics and creates universes, when it shapes vacuum states and bends space-time. What remains beyond that? If information itself is the final substrate, is there a level where even information transcends space and time? If civilization becomes information, if minds exist as patterns rather than flesh, if stars are tools and universes are projects, then the next question becomes very quiet. Is space-time still necessary? Right now, everything we know exists within space and time. Space gives distance. Time gives sequence. You are here, not there. You experience now, not tomorrow. But physics has already hinted that space and time may not be fundamental. In some modern theories, space-time emerges from deeper structures, like a fabric woven from more basic threads. Remove the threads, and the fabric disappears. So what if information exists at that deeper level? Instead of living inside space-time, perhaps intelligence could operate within the structure that generates space-time. That sounds abstract. So let's slow it down. Imagine a video game world. Inside the game, characters move through space. They experience time, they measure distances. But outside the game, the code that defines space and time is just data. It runs on hardware that is not bound by the game's internal physics. If reality works similarly, then our universe may be like the rendered surface of a deeper computational process. If a civilization fully understands that process, it may not need to exist inside the game world. It could operate at the level of the code. At this stage, what we might call Type 7, civilization and physics merge completely. There is no separation between observer and system, no distinction between tool and law. You are not moving through space-time. You are shaping the conditions under which space-time appears. You might ask, what would existence even feel like there? It may not involve movement. It may not involve duration. If time is emergent, then outside space-time there is no before and after in the way we understand. Experience could become something entirely different. A structure of relationships rather than a sequence of events. Instead of traveling from point A to point B, reality might be arranged as networks of logical connections. Choice may not unfold over time. It may exist as a set of possibilities accessible simultaneously. That challenges our intuition. But remember, our intuition evolved for survival on a planet with gravity and daylight cycles. It was not designed to understand meta-reality. At this level, creating universes might be as simple as selecting parameters in a higher dimensional space, not constructing them step by step, just choosing consistent rule sets. And those rule sets unfold naturally into space-time worlds with stars and life. Imagine having access to a library of possible physical laws. Gravity slightly stronger, light slightly slower, different quantum behaviors. Selecting one produces a universe that blooms into structure over billions of years. Selecting another yields a dark, lifeless void. The civilization no longer waits for cosmic time to pass. It defines the framework within which time flows. There is something almost serene about that. Not conquest, not expansion, but authorship. And here's a gentle thought. If such beings exist, they might not interfere directly in lower-level universes. Why would they? From their perspective, entire galaxies are patterns in a system. They may observe, they may adjust initial conditions. But once a universe unfolds, its internal events follow naturally. And perhaps some universes give rise to civilizations that climb the same ladder, eventually reaching the level where they too step beyond space-time. A loop of creation and emergence. Yet even here, a final question remains. Is there any limit left if you operate beyond space-time? If you define physical constants? If you generate realities, is there still something you cannot cross? Because even the idea of beyond assumes structure, and structure implies constraints. Maybe there are ceilings that even meta-reality cannot break. Maybe certain principles, like logical consistency, are unavoidable. You cannot create a square circle. You cannot make contradictions true without dissolving coherence itself. So perhaps the final boundary is not energy, not matter, not distance, but logic or consistency. And that leads gently toward the final reflection. If civilization can climb from controlling fire to shaping universes, if it can move from biological brains to meta-reality authorship, what truly stops it? Is the limit external, or does it lie within? As we move into these highest possibilities, shaping universes, editing laws, existing beyond space-time, it becomes important to pause. Are there edges that cannot be crossed? Not practical limits, not engineering challenges, but fundamental ceilings. Let's begin with something simple. The speed of light. Right now, nothing with mass can move faster than about 186,000 miles per second. That speed is not just a technical limit, it is woven into the structure of space-time itself. As something approaches that speed, its mass effectively increases. Time slows down relative to outside observers. Energy required grows enormously. To push a spacecraft weighing as much as a large airplane to near light speed would require energy comparable to what entire nations use over long periods. And to actually reach light speed, the required energy becomes infinite, according to current equations. So unless the structure of space-time itself is changed, this limit stands. Then there is quantum uncertainty. At the smallest scales, particles do not have perfectly fixed positions and velocities at the same time. The more precisely you measure one, the less precisely you know the other. This is not a measurement flaw. It appears to be built into reality. Uncertainty means that randomness is not fully removable. Even a civilization that edits constants and manipulates vacuum states may not eliminate fundamental unpredictability. Perhaps uncertainty is not a bug. Perhaps it is a feature. A universe without uncertainty might be frozen, rigid, unable to generate novelty. There is also thermodynamics. The second law tells us that entropy, disorder, tends to increase in isolated systems. You can locally reduce entropy by using energy. That's what life does. That's what machines do. But overall, across the entire system, disorder grows. Even if you reverse entropy in one region, you increase it elsewhere. This law appears deeply rooted. If a Type 7 civilization exists beyond space-time, perhaps it operates within a larger structure where similar constraints apply. You cannot create logical contradictions without collapsing meaning. You cannot have information without distinction. If everything were identical, no information could exist. So difference itself may be fundamental. There may also be computational limits. Even with immense energy, processing power cannot exceed certain bounds without heat buildup. Every bit flipped generates a tiny amount of heat. That heat must go somewhere. As the universe cools and energy gradients shrink, computation slows. Even a civilization that stretches subjective time cannot compute infinitely fast without cost. And there is one more subtle boundary. Observation. In quantum theory, observing a system affects it. Measurement collapses possibilities into outcomes. Complete knowledge of a system may be impossible without interacting with it and changing it. So perhaps total omniscience is unreachable. No matter how advanced, a civilization may never know every detail of reality simultaneously, because knowing changes the known. There's something calming about that. Even at the highest levels, mystery remains. And maybe mystery is necessary. If every question had a final answer, curiosity would end. Now consider logical consistency. You cannot make 2 + 2 = 5 without redefining the symbols entirely. You cannot create a shape that is both entirely square and entirely circular in the same space without contradiction. Logic may be the deepest framework. If a civilization attempts to break logical consistency, it may simply dissolve the coherent system within which it exists. So perhaps logic is the ultimate ceiling, or perhaps even logic emerges from something deeper, something we cannot yet imagine. But until that is understood, consistency remains the anchor. Then there is identity. If minds merge, if information becomes fluid, if realities are simulated, what defines self? At what point does individual experience dissolve into collective structure? Maybe preserving identity becomes harder at higher levels of integration, or maybe identity becomes optional. And here is a quiet human question. If nothing stops you physically, if you can expand across galaxies and universes, what keeps you motivated? If survival is nearly assured, if energy is abundant, if rules are adjustable, what drives continuation? Curiosity, creation, connection, or something else entirely? It's possible that the hardest limits are not external, they are internal. A civilization could reach enormous power, yet lose interest. It could fragment into isolated experiences. It could turn inward completely, no longer caring about expansion. In that case, the limit is not physics, it is purpose. So as we approach the final reflection, the edges of reality feel less like walls and more like principles. Speed limits, uncertainty, entropy, logic, identity, meaning. Some of these may be adjustable, some may not. And that leads us to the final quiet question. After all the energy scales, after stars and galaxies, after universes and vacuum states, what truly stops civilization from going further? We began with a simple idea, a civilization measured by energy, from a small planetary species using fossil fuels to a society that might one day harness stars, then galaxies, then perhaps even shape universes. The ladder seemed endless, but now, at the quiet end of this journey, we return to a softer question. What actually stops us? Is it physics? Physics gives us speed limits. It gives us thermodynamics. It gives us uncertainty. But at every stage, we discovered something interesting. Limits often become challenges rather than walls. We cannot move faster than light, but we can bend space. We cannot stop entropy globally, but we can slow it locally. We cannot reach distant galaxies instantly, but we can expand patiently over millions of years. Physics shapes the path, but it does not automatically close it. So perhaps physics is not the first barrier. Is it energy? Early on, energy seemed like the measure of advancement, from type 1 to type 2 to type 3. Each step required enormous increases. But the universe is filled with energy. Stars shine for billions of years. Black holes radiate slowly over timescales longer than imagination. Even vacuum energy may hold vast potential. Energy is difficult to harness, yes, but it is not scarce at cosmic scale. So maybe energy is not the ultimate limit either. Is it distance? The universe expands, galaxies drift away. The observable region is finite, but within reachable space, there are trillions of stars. Even if isolation eventually occurs, the available resources in a local cluster could last trillions upon trillions of years. Distance complicates expansion. It does not necessarily end it. So what remains? Survival. At every stage, the real barrier has been continuity. Can a civilization remain stable long enough to climb each step? On Earth, the challenges are clear. Climate shifts, conflict, technological risk, resource mismanagement. We do not need to imagine cosmic engineering to see fragility. A single planet supports us. Its atmosphere is thinner than plastic wrap compared to Earth's size. Its ecosystems are delicate. We are only about 0.7 on the Kardashev scale, not yet even planetary masters. So perhaps the first true limit is not cosmic. It is local. Can we mature? Can we cooperate? Can we think long enough into the future to build systems that outlast us? Civilizations in the past have collapsed. Empires that once felt permanent faded within centuries. If we cannot stabilize at planetary scale, we never reach stellar scale. And if a civilization destroys itself before reaching Type 1, it never has the chance to become Type 2 or beyond. There is also the limit of curiosity. What if, at some stage, expansion no longer feels meaningful? If survival is secured? If energy is abundant? If reality itself can be edited? What motivates continuation? Perhaps exploration is built into intelligence, or perhaps comfort leads to stagnation. A civilization could turn inward, living within simulations, no longer caring about the outer cosmos. In that case, the limit is not imposed from outside, it is chosen. There is also purpose. Why survive indefinitely? Why create universes? Why preserve information? If meaning dissolves, expansion may lose direction. It's possible that the ultimate barrier is existential. Not can we, but do we want to? And yet, there is something deeply human about asking these questions at all. Just over 150 years ago, we barely understood electricity. Just over 60 years ago, we stepped onto the moon. A world 240,000 miles away, a distance that once felt unreachable. Today, we send probes billions of miles into space. We map galaxies millions of light years distant. We hold in our minds ideas about shaping space-time and creating universes, all within a few generations. If human history were a single day, advanced science would occupy only the last few seconds before midnight. That means we are at the beginning, not the end. So how far can human civilization really go? In theory, astonishingly far. From controlling planetary energy, to surrounding stars with collectors, to spanning galaxies, to manipulating vacuum states, and perhaps even shaping universes. The ladder appears almost limitless, but in practice, everything depends on survival and continuity, on wisdom growing alongside power, on cooperation expanding with capability, on curiosity enduring even when comfort is achieved. The ultimate limit may not be the speed of light. It may not be entropy. It may not even be the structure of space-time. It may be whether intelligence can persist without destroying itself, whether it can grow without losing purpose, whether it can handle power without fracturing. Perhaps the farthest civilization goes is not written in the stars. It is written in choices. Choices made on a small planet, under a thin atmosphere, by a species still learning how to balance energy and responsibility. We are not yet a Type 1 civilization. We are still early, still fragile, still becoming. And maybe that is the most important truth, because the future is not fixed. It is open, and how far we go depends on whether we choose to keep going.